Hi everybody and welcome to lesson 7. We're going to start by having a look at a kind of regularization called weight decay. And the issue that we came to at the end of the last lesson is that we were training our simple dot product model with bias, and our loss started going down and then it started going up again. And so we have a problem that we are overfitting. And remember, in this case, we're using mean squared error. So try to recall why it is that we don't need a metric here, because mean squared error is pretty much the thing we care about, really. Or we could use mean absolute error if we like, but either of those works fine as a loss function. They don't have the problem of big flat areas like accuracy does for classification. So what we want to do is to make it less likely that we're going to overfit by doing something we call reducing the capacity of the model. The capacity of the model is basically how much space does it have to find answers. And if it can kind of find any answer anywhere, those answers can include basically memorizing the data set. So one way to handle this would be to decrease the number of latent factors. But generally speaking, reducing the number of parameters in a model, particularly as we look at more deep learning style models, ends up biasing the models towards very simple kind of shapes. So there's a better way to do it. Rather than reducing the number of parameters, instead we try to force the parameters to be smaller unless they're really required to be big. And the way we do that is with weight decay. Weight decay is also known as L2 regularization. They're very slightly different, but we can think of them as the same thing. And what we do is we change our loss function. And specifically, we change the loss function by adding to it the sum of all the weights squared. In fact, all of the parameters squared, really should say. Why do we do that? Well, because if that's part of the loss function, then one way to decrease the loss would be to decrease the weights. One particular weight or all of the weights or something like that. And so when we decrease the weights, if you think about what that would do, then think about, for example, the different possible values of a in y equals ax squared. The larger a is, for example, a is 50, you get these very narrow peaks. In general, big coefficients are going to cause big swings, big changes in the loss, the small changes in the parameters. And when you have these kind of sharp peaks or valleys, it means that a small change to the parameter can make a small change to the input can make a big change to the loss. And so if you're in that situation, then you can basically fit all the data points close to exactly with a really complex, jagged function with sharp changes, which exactly tries to sit on each data point rather than finding a nice smooth surface which connects them all together or goes through them all. So if we limit our weights by adding in to the loss function the sum of the weights squared, then what it's going to do is it's going to fit less well on the training set because we're giving it less room to try anything that it wants to. But we're going to hope that it would result in a better loss on the validation set or the test set, so that it will generalize better. One way to think about this is that the loss with weight decay is just the loss plus the sum of the parameters squared times some number we pick, a hyperparameter. Sometimes it's like 0.1 or 0.01 or 0.001 kind of region. So this is basically what loss with weight decay looks like in an equation. But remember, when it actually comes to how is the loss used in stochastic gradient descent, it's used by taking its gradient. So what's the gradient of this? Well, if you remember back to when you first learnt calculus, and it's okay if you don't, the gradient of something squared is just 2 times that something. We've changed from parameters to weight, which is a bit confusing. So just use weight here to keep it consistent. Maybe parameters is better. So the derivative of weight squared is just 2 times weight. So in other words, to add in this term to the gradient, we can just add to the gradient's weight decay times 2 times weight. And since weight decay is just a hyperparameter, we can just replace it with weight decay times 2. So that would just give us weight decay times weight. So weight decay refers to adding on to the gradients, the weights times some hyperparameter. And so that is going to try to create these kind of more shallow, less bumpy surfaces. So to do that, we can simply, when we call fit or fit1cycle or whatever, we can pass in a WD parameter, and that's just this number here. So if we pass in 0.1, then the training loss goes from 0.29 to 0.49. So it's much worse, right? Because we can't overfit anymore. But the valid loss goes from 0.89 to 0.82. Much better. So this is an important thing to remember for those of you that have done a lot of more traditional statistical models. Is in kind of more traditional statistical models, we try to avoid overfitting and we try to increase generalization by decreasing the number of parameters. But in a lot of modern machine learning and certainly deep learning, we tend to instead use regularization, such as weight decay, because it gives us more flexibility. It lets us use more nonlinear functions and still avoid, still reduces the capacity of the model. Great. So we're down to 0.823. This is a good model. This is really actually a very good model. And so let's dig into actually what's going on here, because in our architecture, remember, we basically just had 4 embedding layers. So what's an embedding layer? We've described it conceptually, but let's write our own. And remember, we said that an embedding layer is just a computational shortcut for doing a matrix multiplication by a one-hot encoded matrix, and that is actually the same as just indexing into an array. So an embedding is just a indexing into an array. And so it's nice to be able to create our own versions of things that exist in PyTorch and fast.ai. So let's do that for embedding. So if we're going to create our own kind of layer, which is pretty cool, we need to be aware of something, which is normally a layer is basically created by inheriting, as we've discussed, from module or nn.module. So for example, this is an example here of a module where we've created a class called T that inherits from module. And when it's constructed, remember that's what dunder init does, we're just going to set, this is just a dummy little module here. We're going to set self.a to the number 1 repeated 3 times as a tensor. Now, if you remember back to Notebook 4, we talked about how the optimizers in PyTorch and fast.ai rely on being able to grab the parameters attribute to find a list of all the parameters. Now, if you want to be able to optimize self.a, you would need it to appear in parameters, but actually there's nothing there. Why is that? That's because PyTorch does not assume that everything that's in a module is something that needs to be learnt. To tell it that it's something that needs to be learnt, you have to wrap it with nn.parameter. So here's exactly the same class, but torch.ones, which is just a list of three ones, in this case, is wrapped in nn.parameter. And now if I go parameters, I see I have a parameter with 3 ones in it. And that's going to automatically call requires grad underscore for us as well. We haven't had to do that for things like nn.linear in the past, because PyTorch automatically uses nn.parameter internally. So if we have a look at the parameters for something that uses nn.linear with no bias layer, you'll see again we have here a parameter with 3 things in it. So we want to, in general, be able to create a parameter, so something with a tensor with a bunch of things in, and generally we want to randomly initialize them So to randomly initialize, we can pass in the size we want. We can initialize a tensor of zeros of that size, and then randomly generate some normally distributed random numbers with a mean of 0, standard deviation of 0.01. No particular reason I'm picking those numbers, just to show how this works. So here's something that will give us back a set of parameters of any size we want. And so now we're going to replace everywhere that used to say embedding, I'm going to replace it with create params. Everything else here is the same in the init, under init. And then the forward is very, very similar to before. As you can see, I'm grabbing the 0 index column from X, that's my users, and I just look it up, as you see, in that user factors array. And the cool thing is I don't have to do anything with gradients myself for this manual embedding layer, because PyTorch can figure out the gradients automatically, as we've discussed. So then I just got the dot product as before, add on the bias as before, do the sigmoid range as before. And so here's a dot product bias without any special PyTorch layers, and we fit, and we get the same result. So I think that is pretty amazingly cool. We've really shown that the embedding layer is nothing fancy, it's nothing magic, right? It's just indexing into an array. So hopefully that removes a bit of the mystery for you. So let's have a look at this model that we've created and we've trained and find out what it's learned. It's already useful. We've got something we can make pretty accurate predictions with. But let's find out what the model looks like. So remember when we create...
have a question.
Okay, let's take a question before we look at this.
What's the advantage of creating our own embedding layer over the stock PyTorch one?
Oh, nothing at all. We're just showing that we can. It's great to be able to dig under the surface, because at some point you'll want to try doing new things. So a good way to learn to do new things is to be able to replicate things that already exist, and you can check that you understand how they work. It's also a great way to understand the foundations of what's going on, is to actually create in code your own implementation. But I wouldn't expect you to use this implementation in practice. But basically it removes all the mystery. So if you remember, we've created a learner called learn, and to get to the model that's inside it, you can always call learn.model. And then inside that, there's going to be automatically created for, well, sorry, not automatically, we've created all these attributes, movie factors, movie bias, and so forth. So we can grab learn.model.movieBias. And now what I'm going to do is I'm going to sort that vector, and I'm going to print out the first 5 titles. And so what this is going to do is it's going to print out the movies with the smallest bias. And here they are. What does this mean? Well, it kind of means these are the 5 movies that people really didn't like. But it's more than that. It's not only do people not like them, but if we take account of the genre they're in, the actors they have, you know, whatever the latent factors are, people liked them a lot less than they expected. So maybe, for example, this is kind of, I haven't seen any of these movies, luckily, but perhaps this is a sci-fi movie. So people who kind of like these sci-fi movies found they're so bad they still didn't like it. So we can do the exact opposite, which is to sort ascending. And here are the top 5 movies. And specifically, they're the top 5 by bias, right? So these are the movies that, even after you take account of the fact that LA Confidential, I have seen all of these ones. So LA Confidential is a kind of a murder mystery cop movie, I guess. And people who don't necessarily like that genre, or I think Guy Pearce was in it, so maybe they don't like Guy Pearce very much, whatever, people still liked this movie more than they expect. So this is a kind of a nice thing that we can look inside our model and see what it's learned. And we can look at not only at the bias vector, but we can also look at the factors. Now there are 50 factors, which is too many to visualize. So we can use a technique called PCA, Principal Components Analysis. The details don't matter, but basically they're going to squish those 50 factors down to 3. And then we'll plot the top 2 as you can see here. And what we see when we plot the top two is we can kind of see that the movies have been kind of spread out across a space of some kind of latent factors. And so if you look at the far right, there's a whole bunch of kind of big budget actiony things. And on the far left, there's more like cult kind of things. Fargo, Schindler's List, Monty Python. By the same token, at the bottom, we've got some English Patient, Harry Met Sally, so kind of romance drama kind of stuff. And at the top, we've got action and sci-fi kind of stuff. So you can see, even though we haven't passed in any information about these movies, all we've seen is who likes what. These latent factors have automatically kind of figured out a space or a way of thinking about these movies based on what kinds of movies people like and what other kinds of movies they like along with those. So that's really interesting to kind of try and visualize what's going on inside your model. Now, we don't have to do all this manually. We can actually just say, give me a collab learner using this set of data loaders with this number of factors and this Y range, and it does everything we've just seen. Again, about the same number. Okay, so now you can see, this is nice, right? We've actually been able to see right underneath inside the collab learner part of the fast.ai application, the collaborative filtering application, and we can build it all ourselves from scratch. We know how to create the SGD, know how to create the embedding layer, we know how to create the model, the architecture. So now you can see, we've really can build up from scratch our own version of this. So if we just type learn.model, you can see here the names are a bit more generic. This is a user weight, item weight, user bias, item bias, but it's basically the same stuff we've seen before. And we can replicate the exact analyses we saw before by using this same idea. Okay. Slightly different order this time because it is a bit random, but pretty similar as well. Another interesting thing we can do is we can think about the distance between two movies. So let's grab all the movie factors, or just pop them into a variable. And then let's pick some movie. And then let's find the distance from that movie to every other movie. And so one way of thinking about distance is, you might recall the Pythagorean formula, or the distance on the hypotenuse of a triangle, which is also the distance to a point in a Cartesian plane on a chart, which is root x squared plus y squared. You might know, doesn't matter if you don't, but you can do exactly the same thing for 50 dimensions. It doesn't just work for 2 dimensions. So that tells you how far away a point is from another point if x and y are actually differences between two movie vectors. So then what gets interesting is you can actually then divide that kind of by the length to make all the lengths the same distance to find out how the angle between any two movies. And that actually turns out to be a really good way to compare the similarity of two things. That's called cosine similarity. And so the details don't matter. You can look them up if you're interested. But the basic idea here is to see that we can actually pick a movie and find the movie that is the most similar to it based on these factors. Kind of interesting.
I have a question.
All right.
What motivated learning at a 50-dimensional embedding and then using FA to reduce to 3 versus just learning a 3-dimensional?
Oh, because the purpose of this was actually to create a good model. So the visualization part is normally kind of the exploration of what's going on in your model. And so with 50 latent factors, you're going to get a more accurate. So that's one approach, is this dot product version. there's another version we could use, which is we could create a set of user factors and a set of item factors. And just like before, we could look them up. But what we could then do, instead of doing a .product, we could concatenate them together into a tensor that contains both the user and the movie factors next to each other. And then we could pass them through a simple little neural network. Linear, ReLU, linear. And then sigmoid range as before. So importantly here, the first linear layer, the number of inputs is equal to the number of user factors plus the number of item factors. And the number of outputs is however many activations we have. And then, which maybe we just default to 100 here. And then the final layer will go from 100 to 1 because we're just making one prediction. And so we could create, so we'll call that collab NN. We can instantiate that to create a model. We can create a learner, and we can fit. It's not going quite as well as before. It's not terrible, but it's not quite as good as our .product version. But the interesting thing here is it does give us some more flexibility, which is that since we're not doing a .product, we can actually have a different embedding size for each of users versus items. And actually, fast.ai has a simple heuristic. If you call get embedding size and pass in your data loaders, it will suggest appropriate size embedding matrices for each of your categorical variables. Okay, so each of your user and item tensors. So that's so if we pass in star ems embeddings, that's going to pass in the user tuple and the item tuple, which we can then pass to embedding. This is this star prefix we learned about in the last class, in case you forgot. So this is kind of interesting. We can, we can see here that there's two different architectures we could pick from. It wouldn't be necessarily obvious ahead of time which one's going to work better. In this particular case, the simplest one, the .product one, actually turned out to work a bit better, which is interesting. This particular version here, if you call collab learner and pass useNN equals true, then what that's going to do is it's going to use this version, the version with the concatenation and the linear layers. So collab learner, useNN equals true. Again, we get about the same result as you'd expect because it's just a shortcut for this version. And it's interesting actually, we have a look at collab learner. It actually returns an object of type embedding NN. And it's kind of cool if you look inside the fast.ai source code or use the double question mark trick to see the source code for embedding NN, you'll see it's 3 lines of code. How does that happen? Because we're using this thing called tabular model, which we will learn about in a moment. But basically this neural net version of collaborative filtering is literally just a tabular model in which we pass no continuous variables and some embedding sizes. So we'll see that in a moment. Okay, so that is collaborative filtering. And again, take a look at the further research section in particular after you finish the questionnaire, because there's some really important next steps you can take to push your knowledge and your skills. So let's now move to Notebook 9, Tabular. And we're going to look at tabular modeling and do a deep dive. And let's start by talking about this idea that we were starting to see here, which is embeddings. And specifically, let's move beyond just having embeddings for users and items, but embeddings for any kind of categorical variable. So really, because we know an embedding is just a lookup into an array, it can handle any kind of discrete categorical data. So things like age are not discrete. They're continuous numerical data, but something like sex or postcode are categorical variables. They have a certain number of discrete levels, the number of discrete levels they have is called their cardinality. So to have a look at an example of a data set that contains both categorical and continuous variables, we're going to look at the Rossmann sales competition that ran on Kaggle a few years ago. And so basically what's going to happen is we're going to see a table that contains information about various stores in Germany, and the goal will be to try and predict how many sales there's going to be for each day in a couple of week period for each store. So one of the interesting things about this competition is that one of the gold medalists used deep learning, and it was one of the earliest known examples of a state-of-the-art deep learning tabular model. I mean, this is not long ago, maybe 2015 or something, but really this idea of creating state-of-the-art tabular models with deep learning has not been very common and for not very long. Interestingly, compared to the other gold medalists in this competition, the folks that used deep learning used a lot less feature engineering and a lot less domain expertise. And so they wrote a paper called Entity Embeddings of Categorical Variables, in which they basically described the exact thing that you saw in Notebook 8, the way you can think of one-hot encodings as just being embeddings, you can concatenate them together, and you can put them through a couple of layers. They call them dense layers, we call them linear layers, and create a neural network out of that. So this is really a neat, kind of simple and obvious in hindsight trick. And they actually did exactly what we did in the paper, which is to look at the results of the trained embeddings. And so, for example, they had an embedding matrix for regions in Germany, because there wasn't really metadata about this. These were just learnt embeddings, just like we learnt embeddings about movies. And so then they just created, just like we did before, a chart where they popped each region according to, I think, probably a PCA of their embeddings. And then if you circle the ones that are close to each other in blue, you'll see that they're actually close to each other in Germany. And ditto for red, and ditto for green. And then here's the brown. So this is like pretty amazing, is the way that we can see that it's kind of learnt something about what Germany looks like, based entirely on the purchasing behavior of people in those states. Something else they did was to look at every store, and they looked at the distance between stores in practice, like how many kilometers away they are. And then they looked at the distance between stores in terms of their embedding distance, just like we saw in the previous notebook. And there was this very strong correlation that stores that were close to each other physically ended up having close embeddings as well, even though the actual location of these stores in physical space was not part of the model. Ditto with days of the week. So the days of the week were another embedding, and the days of the week that were next to each other ended up next to each other in embedding space, and ditto for months of the year. So pretty fascinating the way kind of information about the world ends up captured just by looking at training embeddings, which, as we know, are just index lookups into an array. So the way we then combine these categorical variables with these embeddings with continuous variables, what was done in both the entity embedding paper that we just looked at, and then also described in more detail by Google when they described how their recommendation system in Google Play works. This is from Google's paper, is they have the categorical features that go through the embeddings, and then there are continuous features, and then all the embedding results and the continuous features are just concatenated together into this big concatenated table that then goes through, in this case, 3 layers of a neural net. And interestingly, they also take the kind of collaborative filtering bit and do the dot product as well and combine the two. So they use both of the tricks we used in the previous notebook and combine them together. So that's the basic idea we're going to be seeing for moving beyond just collaborative filtering, which is just two categorical variables, to as many categorical and as many continuous variables as we like. But before we do that, let's take a step back and think about other approaches. Because as I mentioned, the idea of deep learning as a kind of a best practice for tabular data is still pretty new, and it's still kind of controversial. It's certainly not always the case that it's the best approach. So when we're not using deep learning, what would we be using? Well, what we'd probably be using is something called an ensemble of decision trees. And the two most popular are random forests and gradient boosting machines or something similar. So basically between multi-layered neural networks learned with SGD and ensembles of decision trees, that kind of covers the vast majority of approaches that you're likely to see for tabular data. And so we're going to make sure we cover them both, of course, today, in fact. So although deep learning is nearly always clearly superior for stuff like images and audio and natural language text, these two approaches tend to give somewhat similar results a lot of the time for tabular data. So let's take a look. You really should generally try both and see which works best for you for each problem you look at.
Why does the range go from 0 to 5.5 if the maximum is 5?
That's a great question. The reason is, if you think about it for sigmoid, it's actually impossible for a sigmoid to get all the way to the top or all the way to the bottom. Those are asymptotes. So no matter how big your x is, it can never quite get to the top, or no matter how small it is, it can never quite get to the top. So if you want to be able to actually predict a rating of 5, then you need to use something higher than 5, your maximum.
Are embeddings used only for highly cardinal categorical variables, or is this approach used in general? For low cardinality, can one use a one-hot encoding?
So I'll remind you, cardinality is the number of discrete levels in a variable. And remember that an embedding is just a computational shortcut for a one-hot encoding. So there's really no reason to use a one-hot encoding, because it's as long as you have more than 2 levels, it's always going to be more memory and slower and give you exactly mathematically the same thing. And if there's just 2 levels, then it is basically identical. So there isn't really any reason not to use it. Thank you for those great questions. Okay, so one of the most important things about decision tree ensembles is that at the current state of the technology, they do provide faster and easier ways of interpreting the model. I think that's rapidly improving for deep learning models on tabular data, but that's where we are right now. They also require less hyperparameter tuning, so they're easier to kind of get right the first time. So my first approach for analyzing a new tabular data set is always an ensemble of decision trees. And specifically, I pretty much always start with a random forest because it's just so reliable. Yes?
Your experience for highly imbalanced data, such as fraud or medical data, what usually works best out of random forest, XGBoost, or neural network?
I'm not sure that whether the data is balanced or unbalanced is a key reason for choosing one of those above the others. I would try all of them and see which works best. So the exception to the guideline about start with decision tree ensembles as your first thing to try would be if there's some very high cardinality categorical variables, then they can be a bit difficult to get to work really well in decision tree ensembles. Or if there's something like, most importantly, if it's like plain text data or image data or audio data or something like that, then you're definitely going to need to use a neural net in there, but you could actually ensemble it with a random forest, as we'll see. Okay, so clearly we're going to need to understand how decision tree ensembles work. So PyTorch isn't a great choice for decision tree ensembles. They're really designed for gradient-based methods, and random forests and decision tree growing are not really gradient-based methods in the same way. So instead, we're going to use a library called scikit-learn, which is referred to as sklearn as a module. Scikit-learn does a lot of things. We're only going to touch on a tiny piece of them. Stuff we need to do to train decision trees and random forests. We've already mentioned before Wes McKinney's book, also a great book for understanding more about scikit-learn. So the data set for learning about decision tree ensembles is going to be another data set. It's called the Blue Book for Bulldozers data set, and it's a Kaggle competition. So Kaggle competitions are fantastic. They are machine learning competitions where you get interesting data sets, you get feedback on whether your approach is any good or not. You can see on a leaderboard what approaches are working best, and then you can read blog posts from the winning contestants sharing tips and tricks. It's certainly not a substitute for actual practice doing end-to-end data science projects, but for becoming good at creating predictive models that are predictive, it's a really fantastic resource, highly recommended. And you can also submit to most old competitions to see how you would have gone without having to worry about, the kind of stress of like whether people will be looking at your results because they're not publicized or published if you do that. Yes.
There's a question.
Sure.
Can you comment on real-time applications of random forest? My experience, they tend to be too slow for real-time use cases like a recommender system. Neural network is much faster when run on the right hardware.
Well, let's get to that once we've seen what they are, shall we? Now, you can't just download and untar Kaggle datasets using the untar data thing that we have in fast.ai. So you actually have to sign up to Kaggle and then follow these instructions for how to download data from Kaggle. Make sure you replace creds here with what it describes. You need to get a special API code and then run this one time to put that up on your server. And now you can use Kaggle to download data using the API. So after we do that, we're going to end up with a bunch of, as you see, CSV files. So let's take a look at this data. So the main data, the main table is train.csv. Remember, that's comma-separated values. And the training set contains information such as unique identifier of a sale, the unique identifier of a machine, the sale price, the sale date. So what's going on here is one row of the data represents a sale of a single piece of heavy machinery, like a bulldozer, at an auction. So it happens at a date, has a price, it's of some particular piece of equipment, and so forth. So if we use pandas again to read in the CSV file, let's combine training and valid together. We can then look at the columns to see there's a lot of columns there, and many things which I don't know what the hell they mean, like blade extension and pad type and ride control. But the good news is we're going to show you a way that you don't have to look at every single column and understand what they mean. And random forests are going to help us with that as well. So once again, we're going to be seeing this idea that models can actually help us with data understanding and data cleanup. One thing we can look at is ordinal columns, a good place to look at that now. If there's things there that you know are discrete values but have some order, like product size, it has medium and small and large, medium and mini, these should not be in alphabetical order or some random order. They should be in this specific order, right? They have a specific ordering. So we can use as type to turn it into a categorical variable, and then we can say set categories ordered equals true to basically say this is an ordinal column. So it's got discrete values, but we actually want to define what the order of the classes are. We need to choose which is the dependent variable, and we do that by looking on Kaggle. And Kaggle will tell us that the thing we're meant to be predicting is sale price. And actually, specifically, they'll tell us the thing we're meant to be predicting is the log of sale price, because root mean squared log error is the what we're actually going to be judged on in the competition. So we take the log. So we're just going to replace sale price with its log, and that's what we'll be using from now on. So a decision tree ensemble requires decision trees. So let's start by looking at decision trees. So a decision tree in this case is something that asks a series of binary, that is yes or no questions about data. So such as, is somebody less than 30? Yes, they are. Are they eating healthily? Yes, they are. And so, okay, then we're going to say they're fit or unfit. So like there's an example of some arbitrary decision tree that somebody might have come up with. It's a series of binary yes and no choices, and at the bottom are leaf nodes that make some prediction. Now, of course, for our bulldozers competition, we don't know what binary questions to ask about these things and in what order in order to make a prediction about sale price. So we're doing machine learning, so we're going to try and come up with some automated way to create the questions. And there's actually a really simple procedure for doing that. You have a think about it. So if you want to kind of stretch yourself here, have a think about what's an automatic procedure that you can come up with that would automatically build a decision tree where the final answer would do a, significantly better than random job of estimating the sale price of one of these auctions. All right, so here's the approach that we could use. Loop through each column of the data set. So we're going to go through each of, well, obviously not sale price, that's a dependent variable, sale ID, machine ID, auctioneer, year made, etc. And so one of those will be, for example, product size. And so then what we're going to do is we're going to loop through each possible value of product size. Large, medium, etc. And then we're going to do a split, basically like where this comma is. And we're going to say, okay, let's get all of the auctions of large equipment and put that into one group, and everything that's smaller than that and put that into another group. And so that's here, split the data into two groups based on whether they're greater than or less than that value. If it's a categorical non-ordinal variable, it'll be just whether it's equal or not equal to that level. And then we're going to find the average sale price for each of the two groups. So for the large group, what was the average sale price? For the smaller than large group, what was the average sale price? And that will be our model. Our prediction will simply be the average sale price for that group. And so then you can say, well, how good is that model? If our model was just to ask a single question with a yes-no answer, put things into two groups and take the average of the group as being our prediction, then we can say, how good would that model be? What would be the root mean squared error from that model? And so we can then say, all right, how good would it be if we used large as a split? And then let's try again. What if we did large/medium as a split? What if we did medium as a split? And so in each case, we can find the root mean squared error of that incredibly simple model. And then once we've done that for all of the product size levels, we can go to the next column and look at, have a look, usage band, and do every level of usage band, and then state, every level of state, and so forth. And so there'll be some variable and some split level which gives the best root mean squared error of this really, really simple model. And so then we'll say, okay, that would be our first binary decision. It gives us two groups, and then we're going to take each one of those groups separately and find another single binary decision for each of those two groups using exactly the same procedure. So then we'll have four groups. And then we'll do exactly the same thing again separately for each of those four groups, and so forth. So let's see what that looks like. And in fact, once we've gone through this, you might even want to see if you can implement this algorithm yourself. It's not trivial, but it doesn't require any special coding skills. So hopefully you can find you'll be able to do it. There's a few things we have to do before we can actually create a decision tree in terms of just some basic data munging. One is, if we're going to take advantage of dates, we actually want to call fast.ai's add date part function. And what that does, as you see after we call it, is it creates a bunch of different bits of metadata from that data, say your year, say your month, say your week, say your day, and so forth. So sale date of itself doesn't have a whole lot of information directly, but we can pull lots of different information out of it. And so this is an example of something called feature engineering, which is where we take some piece of data and we try to create lots of other pieces of data from it. So is this particular date the end of a month or not? Is it the end of a year or not? And so forth. So that handles dates. There's a bit more cleaning we want to do, and fast.ai provides some things to make cleaning easier. We can use the Tabular pandas class to create a tabular data set using pandas. And specifically, we're going to use two tabular processors, or tabular procs. A tabular processor is basically just a transform. And we've seen transforms before, so go back and remind yourself what a transform is. Except it's just slightly different. It's like 3 lines of code, if you look at the code for it. It's actually going to modify the object in place rather than creating a new object and giving it back to you. And that's because often these tables of data are kind of really big and we don't want to waste lots of RAM. And it's just going to run the transform once and save the result rather than doing it lazily when you access it. For the same reason, we're just trying to make this a lot faster. So you can just think of them as transforms, really. So one of them is called categorify, and categorify is going to replace a column with numeric categories using the same basic idea of like a vocab like we've seen before. Fill missing is going to find any columns with missing data, and it's going to fill in the missing data with the median of the data and create a new column, new Boolean column, which is set to true for anything that was missing. So these two things is basically enough to get you to a point where most of the time you'll be able to train a model. Now the next thing we need to do is think about our validation set. As we discussed in lesson 1, a random validation set is not always appropriate. And certainly for something like predicting auction results, it almost certainly is not appropriate, because we're going to be wanting to use a model in the future, not at some random date in the past. So the way this Kaggle competition was set up was that the test set, the thing that you had to fill in and submit for the competition, was 2 weeks of data that was after any of the training set. So we should do the same thing for a validation set. We should create something which is where the validation set is the last couple of weeks of data. And so then the training set will only be data before that. So we basically can do that by grabbing everything before October 2011, create our training and validation set based on that condition, and grabbing those bits. So that's going to split our training set and validation set by date, not randomly. We're also going to need to tell, when you create a tabular pandas object, you're going to be passing in a data frame, you're going to be passing in your tabular procs, and you also have to say, what are my categorical and continuous variables? We can use fast.ai's cont.cat split to automatically split a data frame to continuous and categorical variables for you. So we can just pass those in. Tell it what is the dependent variable, you can have more than one, and what are the indexes to split into training and valid. And this is a tabular object. So it's got all the information you need about the training set, the validation set, categorical and continuous variables, and the dependent variable, and any processes to run. It looks a lot like a datasets object, but it has a .train, it has a .valid, and so if we have a look at .show, we can see the data. But .show is going to show us the kind of the string data. But if we look at .items, you can see internally it's actually stored these very compact numbers, which we can use directly in a model. So fast.ai has basically got us to a point here where we have our data into a format ready for modeling, and our validation set's being created to see how these numbers relate to these strings. We can, again, just like we saw last week, use the classes attribute, which is a dictionary, which basically tells us the vocab. So this is how we look up, for example, 6 is 0, 1, 2, 3, 4, 5, 6. This is compact example. That processing takes a little while to run, so you can go ahead and save the tabular object, and so then you can load it back later without having to rerun all the processing. So that's a nice kind of fast way to quickly get back up and running without having to reprocess your data. So we've done the basic data munging we need. So we can now create a decision tree, and in scikit-learn, a decision tree where the dependent variable is continuous is a decision tree regressor. And let's start by telling it we just want a total of 4 leaf nodes. We'll see what that means in a moment. And in scikit-learn, you generally call fit, so it looks quite a lot like fast.ai, and you pass in your independent variables and your dependent variable. And we can grab those straight from our tabular object training set as .x's and .y, and we can do the same thing for validation, just to save us some typing. Okay, question.
Do you have any thoughts on what data augmentation for tabular data might look like?
I don't have a great sense of data augmentation for tabular data. We'll be seeing later, either in this course or in the next part, drop out and mix up and stuff like that, which there might be opportunity to do that in later layers in a tabular model. Otherwise, I think you'd need to think about kind of the semantics of the data and think about what are things you could do to change the data without changing the meaning. Sounds like a pretty tricky route.
Their question, does fast.ai distinguish between ordered categories, such as low, medium, high, and unordered categorical variables?
Yes, that was that ordinal thing I told you about before. And all it really does is it ensures that your classes list has a specific order. So then these numbers actually have a specific. And as you'll see, that's actually going to turn out to be pretty important for how we train our random forest. Okay, so we can create a decision tree regressor, we can fit it, and then we can draw it, the fast.ai function. And here is the decision tree we just trained. And behind the scenes, this actually used basically the exact process that we described back here, right? So this is where you can like try and create your own decision tree implementation if you're interested in stretching yourself. So we're going to use one that's already exists, and the best way to understand what it's done is to look at this diagram from top to bottom. So the first step is it says like, okay, the initial model it created is a model with no binary splits at all. Specifically, it's always going to predict the value 10.1 for every single row. Why is that? Well, because this is the simplest possible model, is to take the average of the dependent variable and always predict that. And so this is always should be your kind of pretty much your basic baseline for regression. There are 404,710 rows, auctions, that we're averaging. And the mean squared error of this incredibly simple model, in which there are no rules at all, no groups at all, just a single average, is a 0.48. So then, the next most complex model is to take a single column, coupler system, and a single binary decision, is coupler system less than or equal to 0.5. True, there are 360,847 auctions where it's true. and 43,863 where it's false. And now interestingly, in the false case, you can see that there are no further binary decisions. So this is called a leaf node. It's a node where this is as far as you can get. And so if your coupler system is not less than or equal to 0.5, then the prediction this model makes for your sale price is 9.21. Versus if it's true, it's 10.21. So you can see it's actually found a very big difference here, and that's why it picked this as the first binary split. And so the mean squared error for this section here is 0.12, which is far better than we started out at, 0.48. This group still has 360,000 in it, and so it does another binary split. This time is the year that this piece of equipment made, was it less than or equal to 1991 and a half? If it's true, then we get a leaf node, and the prediction is 9.97, mean squared error 0.37. If the value is false, we don't have a leaf node, and we have another binary split. And you can see eventually we get down to here, coupler system true, year made false, product size false, mean squared error 0.17. So all of these leaf nodes have MSEs that are smaller than that original baseline model of just taking the mean. So this is how you can grow a decision tree. And we only stopped here because we said max leaf nodes is 4. 1, 2, 3, 4, right? And so if we want to keep training it further, we can just use a higher number. There's actually a very nice library by Terence Parr called dtreeviz, which can show us exactly the same information like so. And so here are the same leaf nodes, 1, 2, 3, 4. And you can see the kind of the chart of how many are there. This is the split, coupler system 0.5. Here are the two groups. You can see the sale price in each of the two groups. And then here's the leaf node. And so then the second split was on year made. And you can see here, something weird's going on with year made. There's a whole bunch of year mades that are 1,000, which is obviously not a sensible year for a bulldozer to be made. So presumably that's some kind of missing value. So when we look at the kind of the picture like this, it can give us some insights about what's going on in our data. And so maybe we should replace those thousands with 1950, because that's, you know, obviously a very, very early year for a bulldozer. So we can kind of pick it arbitrarily. It's actually not really going to make any difference to the model that's created, because all we care about is the order, because we're just doing these binary splits. But it'll make it easier to look at, as you can see. Here's our 1950s now. And so now it's much easier to see what's going on in that binary split. So let's now get rid of max leaf nodes and build a bigger decision tree. And then let's just, for the rest of this notebook, create a couple of little functions. One to create the root mean squared error, which is just here. And another one to take a model and some independent variables, predict from the model on the independent variables, and then take the root mean squared error with a dependent variable. So that's going to be our model's root mean squared error. So for this decision tree, in which we didn't have a stopping criteria, so as many leaf nodes as you like, the model's root mean squared error is 0. So we've just built the perfect model. So this is great news, right? We've built the perfect auction trading system. Well, remember, we actually need to check the validation set. So let's check MRMSE with the validation set, and oh, it's worse than 0. So our training set is 0, our validation set is much worse than 0. Why has that happened? Well, one of the things that a random forest in sklearn can do is it can tell you the number of leaf nodes, the number of leaves. There are 341,000. Number of data points, 400,000. So in other words, we have nearly as many leaf nodes as data points. So most of our leaf nodes only have a single thing in. So they're taking an average of a single thing. And clearly this makes no sense at all. So what we should actually do is pick some different stopping criteria. And let's say, okay, if you get a leaf node with 25 things or less in it, don't don't split, or don't split things to create a leaf node with less than 25 things in it. And now if we fit, and we look at the root mean squared error for the validation set, it's going to go down from 0.33 to 0.32. So the training sets got worse from 0 to 0.248. The validation sets got better, and now we only have 12,000 leaf nodes. So that is much more reasonable. All right, so let's take a 5-minute break, and then we're going to come back and see how we get the best of both worlds. How are we going to get something which has the kind of flexibility to get these, what we're not going to get down to 0, but to get, really deep trees, but also without overfitting. And the trick will be to use something called bagging. We'll come back and talk about that in 5 minutes. Okay, welcome back. So we're going to look at how we can get the best of both worlds, as we discussed. And let's start by having a look at what we're doing with categorical variables, first of all. And so you might notice that previously with categorical variables, for example, in collaborative filtering, we had to kind of think about like how many embedding levels we have, for example. If you've used other modeling tools, you might have experienced things with creating dummy variables, stuff like that. For random forests on the whole, you don't have to. The reason is that, as we've seen, all of our categorical variables have been turned into numbers. And so we can perfectly well have decision tree binary decisions which use those particular numbers. Now, the numbers might not be ordered in any interesting way, but if there's a particular level which kind of stands out as being important, it only takes 2 binary splits to split out that level into a single, into a single piece. So generally speaking, I don't normally worry too much about kind of encoding categorical variables in a special way. As I mentioned, I do try to encode ordinal variables by saying what the order of the levels is, because often, as you would expect, sizes, for example, medium and small are going to be kind of next to each other, and large and extra large would be next to each other. So it's good to have those as similar numbers. Having said that, you can kind of one-hot encode a categorical variable if you want to, using get dummies in pandas. But there's not a lot of evidence that actually helps. That has been stored in a paper. And so I would say in general for categorical variables, don't worry about it too much. Just use what we've shown you. You have a question?
For ordinal categorical variables, how do you deal with when they have like NA or missing values? Where do you put that in the order?
So in fast.ai, NA missing values always appear as the first item. They'll always be the 0 index item. And also if you get something in the validation or test set, which is a level we haven't seen in training, that will be considered to be that missing or NA value as well. All right, so what we're going to do to try and improve our random forest is we're going to use something called bagging. This was developed by a retired Berkeley professor named Leo Breiman in 1994, and he did a lot of great work, and perhaps you could argue that most of it happened after he retired. His technical report was called Bagging Predictors, and he described how you could create multiple versions of a predictor, so multiple different models. And you could then aggregate them by averaging over the predictions. And specifically, the way he suggested doing this was to create what he called bootstrap replicates. In other words, randomly select different subsets of your data, train a model on that subset, kind of store it away as one of your predictors, and then do it again a bunch of times. And so each of these models is trained on a different random subset of your data. And then you to predict, you predict on all of those different versions of your model and average them. It turns out that bagging works really well. So the sequence of steps is basically randomly choose some subset of rows, train a model using that subset, save that model, and then return to step 1. Do that a few times to train a few models. And then to make a prediction, predict with all the models and take the average. That is bagging. And it's very simple, but it's astonishingly powerful. And the reason why is that each of these models we've trained, although they are not using all of the data, so they're kind of less accurate than a model that uses all of the data, each of them is, the errors are not correlated. The errors, because of using that smaller subset, are not correlated with the errors of the other models because they're random subsets. And so when you take the average of a bunch of errors which are not correlated with each other, the average of those errors is 0. So therefore, the average of the models should give us an accurate prediction of the thing we're actually trying to predict. So as I say here, it's an amazing result. We can improve the accuracy of nearly any kind of algorithm by training it multiple times on different random subsets of data and then averaging the predictions. So then Breiman in 2001 showed a way to do this specifically for decision trees, where not only did he randomly choose a subset of rows for each model, but then for each binary split, he also randomly selected a subset of columns. And this is called the random forest. And it's perhaps the most widely used, most practically important machine learning method, and astonishingly simple. To create a random forest regressor, you use sklearn's random forest regressor. If you pass n jobs -1, it will use all of the CPU cores that you have to run as fast as possible. N estimators says how many trees, how many models to train. Max samples says how many rows to use, randomly chosen rows to use in each one. Max features is how many randomly chosen columns to use for each binary split point. Min samples leaf is the stopping criteria, and we'll come back to. So here's a little function that will create a random forest regressor and fit it to some set of independent variables and a dependent variable. So we can give it a few default values and create a random forest and train. And our validation set RMSE is 0.23. If we compare that to what we had before, we had 0.32. So dramatically better by using a random forest. So what's happened when we called random forest regressor is it's just using that decision tree builder that we've already seen, but it's building multiple versions with these different random subsets. And for each binary split it does, it's also randomly selecting a subset of columns. And then when we create a prediction, it is averaging the predictions of each of the trees. And as you can see, it's giving a really great result. And one of the amazing things we'll find is that it's going to be hard for us to improve this very much. The default starting point tends to turn out to be pretty great. The sklearn docs have lots of good information in. One of the things it has is this nice picture that shows as you increase the number of estimators, how does the accuracy improve, error rate improves for different max features levels. And in general, the more trees you add, the more accurate your model. It's not going to overfit, right? Because it's averaging more of these weak models, more of these models that are trained on subsets of the data. So use as many estimators as you like. really just a case of how much time do you have and whether you kind of reach a point where it's not really improving anymore. You can actually get at the underlying decision trees in a model, in a random forest model, using estimators underscore. So with a list comprehension, we can call predict on each individual tree. And so here's an array, a NumPy array, containing the predictions from each individual tree for each row in our data. So if we take the mean across the 0 axis, we'll get exactly the same number. Because remember, that's what a random forest does, is it takes the mean of the trees, predictions. So one cool thing we could do is we could look at the 40 estimators we have and grab the predictions for the first I of those trees and take their mean. And then we can find the root mean squared error. And so in other words, here is the accuracy when you've just got 1 tree, 2 trees, 3 trees, 4 trees, 5 trees, etc. And you can see, so it's kind of nice, right? You can actually create your own, kind of build your own tools to look inside these things and see what's going on. And so we can see here that as you add more and more trees, the accuracy did indeed keep improving, or the root mean squared error kept improving, although the improvement slowed down after a while. The validation set is worse than the training set, and there's a couple of reasons that could have happened. The first reason could be because we're still overfitting, which is not necessarily a problem, it's just something we could identify. Or maybe it's because the fact that we're trying to predict the last 2 weeks is actually a problem, and that the last 2 weeks are kind of different to the other auctions in our data set. Maybe something changed over time. So how do we tell which of those 2 reasons there are? What is the reason that our validation set is worse? We can actually find out using a very clever trick called out-of-bag error, OOB error. And we use OOB error for lots of things. You can grab the OOB error, you can grab the OOB predictions from the model with OOB prediction, and you can grab the RMSE, and you can find that the OOB RMSE is 0.21, which is quite a bit better than 0.23. So let me explain what OOB error is. What OOB error is we look at each row of the training set, not the validation set, each row of the training set, and we say, so if we say for row number 1, which trees included row number 1 in the training? And we'll say, okay, let's not use those for calculating the error because it was part of those trees training. So we'll just calculate the error for that row using the trees where that row was not included in training that tree. Because remember, every tree is using only a subset of the data. So we do that for every row. We find the prediction using only the trees that were not used, that row was not used. And those are the OOB predictions. So in other words, this is like giving us a validation set result without actually needing a validation. But the thing is, it's not with that time offset. It's not looking at the last 2 weeks. It's looking at the whole training set. So this basically tells us how much of the error is due to overfitting versus due to being the last couple of weeks. So that's a cool trick. OOB error is something that very quickly kind of gives us a sense of how much we're overfitting. And we don't even need a validation set to do it. So there's our OOB error. So that's telling us a bit about what's going on in our model. But then there's a lot of things we'd like to find out from our model. And I've got 5 things in particular here, which I generally find pretty interesting, which is how confident are we about our predictions for some particular prediction we're making? Like we can say this is what we think the prediction is, but how confident are we? Is that exactly that, or is it just about that, or we really have no idea? And then for predicting a particular item, which factors were the most important in that prediction and how did they influence it? Overall, which columns are making the biggest difference in our model? Which ones could we maybe throw away and it wouldn't matter? Which columns are basically redundant with each other, so we don't really need both of them? And as we vary some column, how does it change the prediction? So those are the 5 things that I'm interested in figuring out, and we can do all of those things with a random forest. Let's start with the first one. So the first one, we've already seen that we can grab all of the predictions for all of the trees and take their mean to get the actual predictions of the model and then to get the RMSE. But what if instead of saying mean, we did exactly the same thing, like so, but instead said standard deviation? This is going to tell us for every row in our data set, how much did the trees vary? And so if our model really had never seen kind of data like this before, it was something where, you know, different trees were giving very different predictions, it might give us a sense that maybe this is something that we're not at all confident about. And as you can see, when we look at the standard deviation of the trees for each prediction, let's just look at the first 5. They vary a lot, right? 0.2, 0.1, 0.09, nearly 0.3. Okay? So this is a really interesting, it's not something that a lot of people talk about, but I think it's a really interesting approach to kind of figuring out whether we might want to be cautious about a particular prediction because maybe we're not very confident about it. So there's one thing we can easily do with a random forest. The next thing, and this is I think the most important thing for me in terms of interpretation, is feature importance. Here's what feature importance looks like. We can call feature importance on a model with some independent variables. Let's say grab the first 10. And this says these are the 10 most important features in this random forest. These are the things that are the most strongly driving sale price. Or we could plot them. And so you can see here, there's just a few things that are by far the most important. What year the equipment was made, bulldozer or whatever, how big is it, coupler system, whatever that means, and the product class, whatever that means. And so you can get this by simply looking inside your trained model and grabbing the feature importances attribute. And so here, for making it better to print out, I'm just sticking that into a data frame and sorting descending by importance. So how is this actually being done? It's actually really neat. What scikit-learn does, and Bryman, the inventor of random forest, described, is that you can go through each tree and then start at the top of the tree and look at each branch, and at each branch see what feature was used to split, which the binary split was based on which column, and then how much better was the model after that split compared to beforehand. And we basically then say, okay, that column was responsible for that amount of improvement. And so you add that up across all of the splits, across all of the trees for each column, and then you normalize it so they all add to 1, and that's what gives you these numbers, which we show the first few of them in this table and the first 30 of them here in this chart. So this is something that's fast and it's easy, and it kind of gives us a good sense of like, well, maybe the stuff that are less than 0.005 we could remove. So if we did that, that would leave us with only 21 columns. So let's try that. Let's just say, okay, X's which are important are the X's which are in this list of ones to keep. Do the same for valid. Retrain our random forest and have a look at the result. And basically our accuracy is about the same. But we've gone down from 78 columns the 21 column. So I think this is really important. It's not just about creating the most accurate model you can, but you want to kind of be able to fit it in your head as best as possible. And so 21 columns is going to be much easier for us to check for any data issues and understand what's going on. And the accuracy is about the same, or the RMSE. So I would say, okay, let's do that. Let's just stick with X is important from now on. And so here's this entire set of the 21 features. And you can see it looks now like year made and product size are the two really important things. And then there's a cluster of kind of mainly product related things that are kind of at the next level of importance. One of the tricky things here is that we've got like product class desk, model ID, secondary desk, model desk, base model, model descriptor. They all look like there might be similar ways of saying the same thing. So one thing that can help us to interpret the feature importance better and understand better what's happening in the model is to remove redundant features. So one way to do that is to call fast.ai's cluster columns, which is basically a thin wrapper for stuff that scikit-learn already provides. And what that's going to do is it's going to find pairs of columns which are very similar. So you can see here sale year and sale elapsed. See how this line is way out to the right, or else machine ID and model ID is not at all, it's way out to the left. So that means that sale year and sale elapsed are very, very similar. When one is low, the other tends to be low, and vice versa. Here's a group of 3, which all seem to be much the same. And then product group desk and product group, and then FI best base model and FI model desk. So these all seem like things where maybe we could remove one of each of these pairs, because they're basically seem to be much the same. You know, they're when one is high, the other is high, and vice versa. So let's try removing one of each of these. Now it takes a little while to train a random forest, and so just to see whether removing something makes it much worse, we could just do a very fast version. So we could just train something where we only have 50,000 rows per tree, train for each tree. And we'll just use 40 trees. And let's then just get the OOB score. And so for that fast, simple version, our basic OOB with our important X's is 0.877. And here for OOB, a higher number is better. So then let's try going through each of the things we thought we might not need and try dropping them, and then getting the OOB error for our X's with that one column removed. And so compared to 877, most of them don't seem to hurt very much. Sale elapsed hurt quite a bit, right? So for each of those groups, let's go and see which one of the ones seems like we could remove it. So here's the 5 I found. Let's remove the whole lot and see what happens. And so the OOB went from 877 to 874, so hardly any difference at all. Despite the fact we managed to get rid of 5 of our variables. So let's create something called X's final, which is the X is important, and then dropping those 5. Save them for later. We can always load them back again. And then let's check our random forest using those. And again, 0.233 or 0.234. So we've got about the same thing, but we've got even less columns now. So we're getting a kind of a simpler and simpler model without hurting our accuracy, which is great. So the next thing we said we were interested in learning about is for the columns that are, particularly the columns that are most important, what's the relationship between that column and the dependent variable? So for example, what's the relationship between product size and sale price? So the first thing I would do would be just to look at a histogram. So one way to do that is with the value counts in pandas. And we can see here our different levels of product size. And one thing to note here is actually missing is actually the most common. And then next most is compact and small, and then mini is pretty tiny. So we can do the same thing for year made. Now for year made, we can't just see the basic bar chart. Like here I called it a histogram, it's not, it's a bar chart. For year made, we actually need a histogram, which Pandas has stuff like this built in, so we can just call histogram. And that 1950, remember we created it? That's kind of this missing value thing that used to be 1,000. But most of them seem to have been well into the 90s and 2000s. So let's now look at something called a partial dependence plot. I'll show it to you first. Here is a partial dependence plot of year made against partial dependence. And what does this mean? Well, we should focus on the part where we actually have a reasonable amount of data, so at least well into the 80s, so around here. And so let's look at this bit here. Basically what this says is that as year made increases, the predicted sale price, log sale price of course, also increases. You can see. And the log sale price is increasing linearly, on other roughly. So roughly then, this is actually an exponential relationship between year made and sale price. Why do we call it a partial dependence? So we're just plotting the kind of the year against the average sale price? Well, no, we're not. We can't do that because a lot of other things change from year to year. For example, maybe more recently people tend to buy bigger bulldozers or more bulldozers with air conditioning or more expensive models of bulldozers. And we really want to be able to say like, no, just what's the impact of year and nothing else? And if you think about it from a kind of a inflation point of view, you would expect that older bulldozers would be kind of, that bulldozers would get a kind of a constant ratio cheaper the further you go back, which is what we see. So what we really want to say is, all other things being equal, what happens if only the year changes? And there's a really cool way we can answer that question with a random forest. So how does year made impact sale price, all other things being equal? So what we can do is we can go into our actual data set and replace every single value in the year made column with 1950. And then calculate the predicted sale price for every single auction, and then take the average over all the auctions. And that's what gives us this value here. And then we can do the same for 1951, 1952, and so forth, until eventually we get to our final year of 2011. So this isolates the effect of only year made. So it's a kind of a bit of a curious thing to do, but it's a pretty neat trick for trying to kind of pull apart and create this partial dependence to say what might be the impact of just changing year made. And we can do the same thing for product size. Right? And one of the interesting things if we do it for product size is we see that the lowest value of predicted sale price, log sale price, is NA, which is a bit of a worry because we kind of want to know, well, that means it's really important. The question of whether or not the product size is labeled is really important. And that is something that I would want to dig into before I actually use this model to find out, well, why is it that sometimes things aren't labeled and what does it mean? You know, why is it that that's actually such an important predictor? So that is the partial dependence plot, and it's a really clever trick. So we have looked at 4 of the 5 questions we said we wanted to answer at the start of this section. So the last one that we want to answer is this one here. We're predicting with a particular row of data what were the most important factors and how did they influence that prediction. This is quite related to the very first thing we saw. So it's like, imagine you were using this auction price model in real life. You had something on your tablet and you went into some auction and you looked up what the predicted auction price would be for this lot that's coming up to find out whether it seems like it's being under or overvalued, and then you can decide what to do about that. So one thing we said we'd be interested to know is like, well, are we actually confident in our prediction? And then we might be curious to find out like, oh, I'm really surprised it was predicting such a high value. Why was it predicting such a high value? So to find the answer to that question, we can use a module called Tree Interpreter. And Tree Interpreter, the way it works is that you pass in a single row. So it's like, here's the auction that's coming up, here's the model, here's the auctioneer ID, etc., etc. Please predict the value from the random forest. What's the expected sale price? And then what we can do is we can take that one row of data and put it through the first decision tree. And we can see what's the first split that's selected. And then based on that split, does it end up increasing or decreasing the predicted price compared to that kind of raw baseline model of just take the average. And then you can do that again at the next split and again at the next split and again at the next split. So for each split, we see what the increase or decrease in the, addiction, that's not right. We see what the increase or decrease in the prediction is. Fix that while I'm here. Compared to the parent node. And so then you can do that for every tree and then add up the total change in importance by split variable. And that allows you to draw something like this. So here's something that's looking at one particular row of data, and overall we start at 0. And so 0 is the initial 10.1. Do you remember this number? 10.1 is the average log sale price of the whole data set. They call it the bias, the interpreter. And so if we call that 0, then for this particular row we're looking at, year made has a negative 4.2 impact on the prediction. And then product size has a positive 0.2. Coupler system has a positive 0.046. Model ID has a positive 0.127, and so forth, right? And so the red ones are negative and the green ones are positive, and you can see how they all join up until eventually, overall, the prediction is that it's going to be negative 0.122 compared to 10.1, which is equal to 9.98. So this kind of plot is called a waterfall plot. And so basically when we say treeinterpreter.predict, it gives us back the prediction, which is the actual number we get back from the random forest, the bias, which is just always this 10.1 for this data set, and then the contributions, which is all of these different values. It's how important was each factor. And here I've used a threshold, which means anything that was less than 0.08 all gets thrown into this other category. I think this is a really useful kind of thing to have in production because it can help you answer questions, whether it be for the customer or for whoever's using your model. If they're surprised about some prediction, why is that prediction? So I'm going to show you something really interesting using some synthetic data. And I want you to really have a think about why this is happening before I tell you. So I'm going to pause the video if you're watching the video when I get to that point. Let's start by creating some synthetic data like so. So we're going to grab 40 values evenly spaced between 0 and 20. And then we're just going to create the y equals x line and add some normally distributed random jitter around that. Well, here's the scatter plot. So here's some data we want to try and predict. And we're going to use a random forest in a kind of bit of a overkill here. In this case, we only have one independent variable. Scikit-learn expects us to have more than one. So we can use unsqueeze in PyTorch to go from a shape of 40, in other words, a vector with 40 elements, to a shape of 40, 1, in other words, a matrix of 40 rows with one column. So this unsqueeze 1 means add a unit axis here. I don't use unsqueeze very often because I actually generally prefer the index with a special value none. This works in PyTorch and NumPy. And the way it works is to say, okay, xlen, remember that's size, it's a vector of length 40, every row, and then none means insert a unit axis here for the column. So these are two ways of doing the same thing, but this one is a little bit more flexible, so that's what I use more often. So now that we've got the shape that it's expected, which is a rank 2 tensor, an array with 2 dimensions or axes, we can create a random forest, we can fit it, and let's just use the first 30 data points, right? So kind of stop here. And then let's do a prediction, right? So let's plot the original data points and then also plot a prediction. And look what happens on the prediction. It's kind of nice and accurate. And then suddenly, what happens? Okay, so this is the bit where if you're watching the video, I want you to pause and have a think, why is this flat? So, what's gone on here? Well, remember, a random forest is just taking the average of predictions of a bunch of trees. And a tree, the prediction of a tree, is just the average of the values in a leaf node. And remember, we fitted using a training set containing only the first 30. So none of these appeared in the training set. So the highest we could get would be the average of values that are inside the training set. In other words, there's this maximum we can get to. So random forests cannot extrapolate outside of the bounds of the data that they've training set. This is going to be a huge problem for things like time series prediction where there's like an underlying trend, for instance. But really, it's a more general issue than just time variables. It's going to be hard for or impossible often for random forests to just extrapolate outside the types of data that it's seen in a general sense. So we need to make sure that our validation set does not contain out-of-domain data. So how do we find out-of-domain data? So we might not even know if our test set is distributed in the same way as our training data. So if they're from two different time periods, how do you kind of tell how they vary, right? Or if it's a Kaggle competition, how do you tell if the test set and the training set, which Kaggle gives you, have some underlying differences? There's actually a cool trick you can do, which is you can create a column called isValid, which contains 0 for everything in the training set and 1 for everything in the validation set. And it's concatenating all of the independent variables together. So it's concatenating the independent variables for both the training and validation set together. So this is our independent variable, and this becomes our dependent variable. And we're going to create a random forest, not for predicting price, but a random forest that predicts, is this row from the validation set or the training set? So if the validation set and the training set are from kind of the same distribution, if they're not different, then this random forest should basically have 0 predictive power. If it has any predictive power, then it means that our training and validation set are different. And to find out the source of that difference, we can use feature importance. And so you can see here that the difference between the validation set and the training set is, not surprisingly, sale elapsed. So that's the number of days since, I think, like 1970 or something. So it's basically the date. So yes, of course you can predict whether something is in the validation set or the training set by looking at the date, because that's actually how we defined them. That makes sense. This is interesting, sales ID. So it looks like the sales ID is not some random identifier, but it increases over time. And ditto for machine ID. And then there's some other smaller ones here that kind of make sense. So I guess for something like model desk, I guess there are certain models that were only made in later years, for instance. But you can see these top 3 columns are a bit of an issue. So then we could say, like, okay, what happens if we look at each one of those columns, those first 3, and remove them, and then see how it changes our RMSE on our sales price model on the validation set. So we start from point 232, and removing sales ID actually makes it a bit better. Sale elapsed makes it a bit worse, machine ID about the same. So we can probably remove sales ID and machine ID without losing any accuracy, and yep, it's actually slightly improved. But most importantly, it's going to be more resilient over time, right? Because we're trying to remove the time-related features. Another thing to note is that since it seems that this kind of sale elapsed issue, that maybe it's making a big difference, is maybe looking at the sale year distribution. This is the histogram. Most of the sales are in the last few years anyway. So what happens if we only include the most recent few years? So let's just include everything after 2004. So that is X's filtered. And if I train on that subset, then my accuracy improves a bit more from 231 to 230. So that's interesting, right? We're actually using less data, less rows, and getting a slightly better result because the more recent data is more representative. So that's about as far as we can get with our random forest. But what I will say is this issue of extrapolation would not happen with a neural net, would it? Because a neural net is using the underlying layers are linear layers. And so linear layers can absolutely extrapolate. So the obvious thing to think then at this point is, well, maybe would a neural net do a better job of this? That's going to be the thing next after this question.
Question first. How does feature importance relate to correlation?
Feature importance doesn't particularly relate to correlation. Correlation is a concept for linear models, and this is not a linear model. So remember, feature importance is calculated by looking at the improvement in accuracy as you go down each tree and you go down each binary split. If you're used to linear regression, then I guess correlation sometimes can be used as a measure of feature importance. But this is a much more kind of direct version. It's taking account of these non-linearities and interactions and stuff as well. So it's a much more flexible and reliable measure, generally speaking, feature importance. Any more questions? So to do the same thing with a neural network, I'm going to just copy and paste the same lines of code that I had from before, but this time I'll call it NN, DFNN. These are the same lines of code. And I'll grab the same list of columns we had before in the dependent variable to get the same data frame. Now, as we've discussed, for categorical columns, we probably want to use embeddings. So to create embeddings, we need to know which columns should be treated as categorical variables. And as we discussed, we can use cont.cat split for that. One of the useful things we can pass that is the maximum cardinality. So max card equals 9,000 means if there's a column with more than 9,000 levels, you should treat it as continuous. And if it's got less than 9,000 levels, treat it as categorical. So that's, it's a simple little function that just checks the cardinality and splits them based on how many discrete levels they have. And of course, their data type, if it's not actually a numeric data type, it has to be categorical. So there's our split. And then from there, what we can do is we can say, oh, we've got to be a bit careful of sail elapsed, because actually sail elapsed, I think, has less than 9,000 categories, but we definitely don't want to use that as a categorical variable. The whole point was to make it that this is something that we can extrapolate. So we certainly, anything that's kind of time dependent, or we think that we might see things outside the range of inputs in the training data, we should make them continuous variables. So let's make sail elapsed, put it in continuous neural net, and remove it from categorical. So here's the number of unique levels. This is from pandas for everything in our neural net dataset for the categorical variables. And I get a bit nervous when I see these really high numbers. So I don't want to have too many things with like lots and lots of categories. The reason I don't want lots of things with lots and lots of categories is just they're going to take up a lot of parameters, because in an embedding matrix, this is, every one of these is a row in an embedding matrix. In this case, I notice model ID and model desk might be describing something very similar. So I'd quite like to find out if I could get rid of one. And an easy way to do that would be to use a random forest. So let's try removing the model desk. And let's create a random forest. And let's see what happens. And oh, it's actually a tiny bit better, and certainly not worse. So that suggests that we can actually get rid of one of these levels, or one of these variables. So let's get rid of that one. And so now we can create a tabular pandas object just like before. But this time we're going to add one more processor, which is normalize. And the reason we need normalize, so normalize is subtract the mean, divide by the standard deviation. We didn't need that for a random forest, because for a random forest, we're just looking at less than or greater than through our binary splits. So all that matters is the order of things, how they're sorted. It doesn't matter whether they're super big or super small. But it definitely matters for neural nets, because we have these linear layers. So we don't want to have things with kind of crazy distributions with some super big numbers and super small numbers, because it's not going to work. So it's always a good idea to normalize things in neural nets. So we can do that in a tabular neural net by using the normalize tabular proc. So we can do the same thing that we did before with creating our tabular pandas tabular object for the neural net. And then we can create data loaders from that with a batch size. And this is a large batch size because tabular models don't generally require nearly as much GPU RAM as a convolutional neural net or something, or an RNN or something. Since it's a regression model, we're going to want R range. So let's find the minimum and maximum of our dependent variable. Okay, and we can now go ahead and create a tabular learner. So our tabular learner is going to take our data loaders, our Y range, how many activations do you want in each of the linear layers? And so you can have as many linear layers as you like here. How many outputs are there? So this is a regression with a single output. And what loss function do you want? We can use LR find. And then we can go ahead and use fit one cycle. There's no pre-trained model, obviously, because this is not something where people have got pre-trained models for industrial equipment auctions. So we just use fit one cycle and train for a minute. And then we can check. And our RMSE is 0.226, which here was 0.230. So that's amazing. We actually have, straight away a better result than the random forest. It's a little more fussy. It takes a little bit longer. But as you can see, for interesting data sets like this, we can get some great results with neural nets. So here's something else we could do though. The random forest and the neural net, they each have their own pros and cons. There's some things they're good at and there's some they're less good at. So maybe we can get the best of both worlds. And a really easy way to do that is to use ensemble. So we've already seen that a random forest is a decision tree ensemble. So now we can put that into another ensemble. We could have an ensemble of the random forest and a neural net. There's lots of super fancy ways you can do that, but a really simple way is to take the average. So sum up the predictions from the two models, divide by 2, and use that as a prediction. So that's our ensemble prediction, is just literally the average of the random forest prediction and the neural net prediction. And that gives us 0.223 versus 0.226. So how good is that? Well, it's a little hard to say because unfortunately this competition is old enough that we can't even submit to it and find out how we would have gone on Kaggle. So we don't really know. And so we're relying on our own validation set. But it's quite a bit better than even the first place score on the test set. So if the validation set is, doing a good job, then this is a good sign that this is a really, really good model, which wouldn't necessarily be that surprising because, in the last few years, I guess we've learned a lot about building these kinds of models, and we're kind of taking advantage of a lot of the tricks that have appeared in recent years. And yeah, maybe this goes to show that, well, I think it certainly goes to show that both random forests and neural nets have a lot to offer, and try both and maybe even combine both. We've talked about an approach to ensembling called bagging, which is where we train lots of models on different subsets of the data, take the average of. Another approach to ensembling, particularly ensembling of trees, is called boosting. And boosting involves training a small model which underfits your data set. So maybe just have a very small number of leaf nodes. And then you calculate the predictions using the small model. And then you subtract the predictions from the targets. So these are kind of like the errors of your small underfit model. And we call them residuals. And then go back to step 1. But now, instead of using the original targets, use the residuals. So train a small model which underfits your data set, attempting to predict the residuals. Then do that again, until you reach some stopping criterion, such as the maximum number of trees. Now, that will leave you with a bunch of models which you don't average, but which you sum, because each one is creating a model that's based on the residual of the previous one. So we've subtracted the predictions of each new tree from the residuals of the previous tree. So the residuals get smaller and smaller, and then to make predictions, we just have to do the opposite, which is to add them all together. So there's lots of variants of this. But you'll see things like GBMs, or gradient boosted machines, or GBTTs, or gradient boosted decision trees. And there's lots of minor details around, minor and significant details. But the basic idea is what I've shown.
Two questions.
All right, let's take the questions.
So dropping features in a model is a way to reduce the complexity of the model and thus reduce overfitting. Is this better than adding some regularization like weight decay to Tabular?
I didn't claim that we removed columns to avoid overfitting. We removed the columns to simplify fewer things to analyze and it should also mean we don't need as many trees, but there's no particular reason to believe that this will regularize, and the idea of regularization doesn't necessarily make a lot of sense to random forests. You can always add more trees.
Is there a good heuristic for picking the number of linear layers in the tabular model?
Not really. Well, if there is, I don't know what it is. I guess 2. through hidden layers works pretty well. So what I showed, those numbers I showed are pretty good for a large-ish model. By default, it uses 200 and 100, so maybe start with the default and then go up to 500 and 250. If that is an improvement, then just keep doubling them until it stops improving or until you run out of memory or time. Main thing to note about boosted models is that there's nothing to stop us from overfitting. If you add more and more trees to a bagging model, sort of a random forest, it's going to get should generalize better and better, because each time you're using a new model which is based on a subset of the data. But boosting, each model will fit the training set better and better, gradually overfit more and more. So boosting methods do require generally more hyperparameter tuning and fiddling around with things. You certainly have regularization. Boosting. They're pretty sensitive to their hyperparameters, which is why they're not normally my first go-to. But they more often win Kaggle competition. Random forests do. They tend to be good at getting that last little bit of performance. So the last thing I'm going to mention is something super neat, which a lot of people don't seem to know exists. It's a shame because it's super cool, which is something from the entity embeddings paper, the table from it, where what they did was they built a neural network. They got the entity embeddings, EE, and then they tried a random forest using the entity embeddings as predictors, rather than the approach I described with just the raw categorical variables. And the error for a random forest went from 0.16 to 0.11. A huge improvement. And a very simple method, KNN, went from 0.29 to 0.11. Basically, all of the methods, when they used entity embeddings, suddenly improved a lot. The one thing you should try, if you have a look at the further research section after the questionnaire, is it asks to try to do this. Actually take those entity embeddings that we trained in the neural net and use them in the random forest. And then maybe try ensembling again and see if you can beat the 0.223 that we had. Because this is a really nice idea. It's like you get, all the benefits of boosted decision trees, but all of the nice features of entity embeddings. And so this is something that not enough people seem to be playing with for some reason. So overall, random forests are nice and easy to train. They're very resilient. They don't require much pre-processing. They train quickly. They don't overfit. They can be a little less accurate. And they can be a bit slow at inference time, because for inference you have to go through every one of those trees. Having said that, a binary tree can be pretty heavily optimized. It is something you can basically create a totally compiled version of a tree. And they can certainly also be done entirely in parallel. So that's something to consider. Gradient boosting machines are also fast to train on the whole, but a little more fussy about hyperparameters. You have to be careful about overfitting, but a bit more accurate. Neural nets, maybe the fussiest to deal with. They've kind of got the least rules of thumb around or tutorials around saying this is kind of how to do it. It's just a bit newer, a little bit less well understood, but they can give better results in many situations than the other two approaches, or at least with an ensemble can improve the other two approaches. So I would always start with a random forest, and then see if you can beat it using these. So yeah, why don't you now see if you can find a Kaggle competition with tabular data, whether it's running now or it's a past one, and see if you can repeat this process for that and see if you can get in the top 10%. of the private leaderboard. That would be a really great stretch goal at this point. Implement the decision tree algorithm yourself. I think that's an important one. We really understand it. And then from there, create your own random forest from scratch. You might be surprised. It's not that hard. And then go and have a look at the tabular model source code. And at this point, this is pretty exciting. You should find you pretty much know what all the lines do, with 2 exceptions. And if you don't, dig around and explore and experiment and see if you can figure it out. And with that, we are, I am very excited to say, at a point where we've really dug all the way in to the end of these real, valuable, effective fast AI applications, and we're understanding what's going on inside them.
What should we expect for next week?
So for next week, we will at NLP and computer vision, and we'll do the same kind of idea: is delve deep to see what's going on. Thanks, everybody. See you next week. Hi, everybody, and welcome to Lesson 8, the last lesson of Part 1 of this course. Thanks so much for sticking with us. Got a very interesting lesson today where we're going to do a dive into natural language processing. And remind you, we did see natural language processing in Lesson 1. This was it here. We looked at a data set where we could pass in many movie reviews like so and get back probabilities that it's positive or negative sentiment. And we trained it with a very standard looking classifier trainer approach. But we haven't really talked about what's going on behind the scenes there, so let's do that. And we'll also learn about how to make it better. So we were getting about 93%. So 93% accuracy for sentiment analysis, which is actually extremely good, and it only took a bit over 10 minutes. But let's see if we can do better. So we're going to go to notebook number 10. And in notebook number 10, we're going to start by talking about what we're going to do to train an NLP classifier. So a sentiment analysis, which is this movie review positive or negative sentiment, is just a classifier. The dependent variable is binary, and the independent variable is the kind of the interesting bit. So we're going to talk about that. But before we do, we're going to talk about what was the pre-trained model that got used here. Because the reason we got such a good result so quickly is because we're doing fine-tuning of a pre-trained model. So what is this pre-trained model exactly? Well, the pre-trained model is actually a pre-trained language model. So what is a language model? A language model is a special kind of model, and it's a model where we try to predict the next word of a sentence. So for example, if our language model received, even if our language model knows the, then its job would be to predict basics. Now, the language model that we use as our pre-trained model was actually trained on Wikipedia. So we took all the non-trivial sized articles in Wikipedia, and we built a language model which attempted to predict the next word of every sequence of words in every one of those articles. And it was a neural network, of course. And we then take those pre-trained weights, and those are the pre-trained weights that when we said text classifier learner were automatically loaded in. So conceptually, why would it be useful to pre-train a language model? How does that help us to do sentiment analysis, for example? Well, just like an ImageNet model has a lot of information about what pictures look like and what they're consisting of, a language model tells us a lot about what sentences look like and what they know about the world. So a language model, for example, if it's going to be able to predict the end of the sentence, in 1998, this law was passed by President what? So a language model to predict that correctly would have to know a whole lot of stuff. It would have to know about, well, how English language works in general and what kind of sentences go in what places. After the word president would usually be the surname of somebody. It would need to know what country that law was passed in, and it would need to know what president was president of that country in 1998. So it would have to know a lot about the world. It would have to know a lot about language. To create a really good language model is really hard. And in fact, this is something that people spend many, many, many millions of dollars on, creating language models off huge data sets. Our particular one doesn't take particularly long to pre-train, but there's no particular reason for you to pre-train one of these language models because you can download them through fast.ai or through other places. So what happened in lesson 1 is we downloaded this pre-trained Wikipedia model, and then we fine-tuned it. So as per usual, we threw away the last layer, which was specific for predicting the next word of Wikipedia, and fine-tuned the model initially just the last layer to learn to predict sentiment of movie reviews, and then as per usual, then fine-tuned the rest of the model. And that got us 93%. Now, there's a trick we can use, though, which is we start with this Wikipedia language model, and the particular subset we use is called Wikitext 103. And rather than just jumping straight to a classifier, which we did in lesson 1, we can do even better if we first of all create an IMDb language model. That is to say, a language model that learns to predict the next word of a movie review. The reason we do that is that this will help it to learn about IMDb specific kind of words, like it'll learn a lot more about the names of actors and directors. It'll learn about the kinds of words that people use in movie reviews. And so if we do that first, then we would hope we'll end up with a better classifier. So that's what we're going to do in the first part of today's lesson. And we're going to kind of do it from scratch, and we're going to show you how to do a lot of the things from scratch, even though later we'll show you how fast AI does it all for you. So how do we build a language model? So as we point out here, sentences can be different lengths, and documents, like movie reviews, can be very long. So how do we go about this? Well, a word is basically a categorical variable. And we already know how to use categorical variables as an independent variable in a neural net, which was we make a list of all of the possible levels of a categorical variable, which we call the vocab. And then we replace each of those categories with its index, so they all become numbers. We create an initially random embedding matrix for each, so each row then is for one element from the vocab. And then we make that the first layer of a neural net. So that's what we've done a few times now. And we've even created our own embedding layer from scratch, remember? So we can do the same thing with text, right? We can make a list of all the possible words in the whole corpus, the whole data set, and we can replace each word with the index of the vocab and create an embedding matrix. So, in order to create a list of all levels, in this case a list of all possible words, let's first of all concatenate all the documents or the movie reviews together into one big long string and split it into words. Okay, and then our independent variable will basically be that sequence, starting with the first word in the long list and ending with the second last. And our dependent variable will be the sequence of words starting with the second word and ending with the last. So they're kind of offset by 1. So as you move through the first sequence, you're then trying to predict the next word in the second part. That's kind of what we're doing, right? We'll see more detail in a moment. Now, when we create our vocab by finding all the unique words in this concatenated corpus, a lot of the words we see will be already in the embedding matrix, already in the vocab of the pre-trained Wikipedia model, but there's also going to be some new ones, right? There might be some particular actors that don't appear in Wikipedia, or maybe some informal slang words, and so forth. So when we build our vocab and then our embedding matrix for the IMDb language model, any words that are in the vocab of the pre-trained model, we'll just use them as is. But for new words, we'll create a new random vector. So here's the process we're going to have to go through. First, we're going to have to take our big concatenated corpus and turn it into a list of tokens. Could be words, could be characters, could be substrings. That's called tokenization. And then we'll do numericalization, which is basically these two steps, which is replacing each word with its index in a vocab, which means we have to create that vocab. So create the vocab and then convert. Then we're going to need to create a data loader that has lots of substrings, lots of sequences of tokens from our IMDb corpus as an independent variable, and the same thing offset by 1 as a dependent variable. And then we're going to have to create a language model. Now the language model is going to be able to handle input lists that can be arbitrarily big or small. And we're going to be using something called a recurrent neural network to do this, which we'll learn about later. So basically, so far, we've always assumed that everything is a fixed size, a fixed input. So we're going to have to mix things up a little bit here and deal with architectures that can be different sizes. For this notebook, Notebook 10, we're going to kind of treat it as a black box. It's just going to be just a neural net. And then later in the lesson, we'll look at delving inside what's happening in that architecture. Okay, so let's start with the first of these, which is tokenization. So converting a text into a list of words or a list of tokens, what does that mean? Is a full stop a token? What about don't? Is that single word or is it two words? Don't. Or is it, would I convert it to do not? What about long medical words that are kind of made up of lots of pieces of medical jargon that are all stuck together? What about hyphenated words? And really interestingly then, what about something like Polish, where you, or Turkish, where you can create really long words, all the time they create really long words that are actually lots of separate parts all concatenated together. Or languages like Japanese and Chinese that don't use spaces at all. They don't really have a well-defined idea of a word. Well, there's no right answer, but there's basically three approaches. We can use a word-based approach, which is what we use by default at the moment for English, although that might change, which is we split a sentence on space. And then there are some language-specific rules, for example, turning don't into do-n't, and putting punctuation marks as a separate token most of the time. Really interestingly, there are tokenizers that are subword based, and this is where we split words into smaller parts based on the most commonly occurring substrings. We'll see that in a moment. Or, the simplest, character based, split a sentence into its characters. We're going to look at word and subword tokenization in this notebook, and then if you look at the questionnaire at the end, you'll be asked to create your own character-based tokenizer. So please make sure you do that if you can. It'll be a great exercise. So fast.ai doesn't invent its own tokenizers. We just provide a consistent interface to a range of external tokenizers because there's a lot of great tokenizers out there. So you can switch between different tokenizers pretty easily. So let's start. Let's grab our IMDb dataset like we did in lesson 1. And in order to try out a tokenizer, let's grab all the text files. So we can, instead of calling get image files, we'll call get text files. And to have a look at what that's doing, don't forget, we can even look at the source code. And you can see actually it's calling a more general thing called get files and saying what extensions it wants, right? So if anything in fast.ai doesn't work quite the way you want, and there isn't an option which works the way you want, you can often look, or always look underneath to see what we're calling, and you can call the lower level stuff yourself. So files is now a list of files, so we can grab the first one, we can open it, we can read it, have a look at the start of this review, and here it is. Okay, so at the moment, the default English word tokenizer we use is called Spacey, which uses a pretty sophisticated set of rules with special rules for particular words and URLs and so forth. But we're just going to go ahead and say word tokenizer, which will automatically use fast.ai's default word tokenizer, currently Spacey. And so if we pass a list of documents, we'll just make it a list of one document here, to the tokenizer we just created, and just grab the first, since we just created a list, that's going to show us, as you can see, the tokenized version. So you can see here that this movie, which I just discovered at the video store, has, etc. It's changed its into its, and it's put a comma as a separate punctuation mark, and so forth. Okay, so you can see how it has tokenized this review. Let's look at a more interesting one, the US dollar blah blah blah, and you can see here it actually knows that US is special, so it doesn't put the full stop in as a separate place for US. It knows about 1.00 is special. So you can see there's a lot of tricky stuff going on with Spacey to try and be as kind of thoughtful about this as possible. fast.ai then provides this tokenizer wrapper, which provides some additional functionality to any tokenizer, as you can see here, which is, for example, the word it here, which previously was capital IT, has been turned into lowercase it, and then a special token XX Madge has appeared at the front. Everything starting with XX is a special fast.ai token, and this means that the next Madge means that the next word was previously started with a capital letter. So here's another one. This used to be capital T. So we make it lowercase and then add XX Madge. XXBOS means this is the start of a document. So there's a few special rules going on there. So why do we do that? Well, if you think about it, if we didn't lowercase it, for instance, or this, then the capitalized version and the lowercase version are going to be two different words in the embedding matrix, which probably doesn't make sense. You know, regardless of their capitalization, they probably basically mean the same thing. Having said that, sometimes the capitalization might matter. So we kind of want to say, all right, use the same embedding every time you see the word this, but add some kind of marker that says that this was originally capitalized. Okay, so that's why we do it like this. So there's quite a few rules. You can see them in TextProc rules, and you can see the source code. Here's a summary of what they do. But let's look at a few examples. So if we use that tokenizer we created and pass in, for example, this text, you can see the way it's tokenized. We get the XX beginning of stream or beginning of string, beginning of document. This HTML entity has become a real Unicode. We've got the XX Madge we discussed. Now here, www has been replaced by xxrep3w. That means the letter W is repeated 3 times. So for things where you've got like, 100 exclamation marks in a row, or the word so with like 50 O's, this is a much better representation. And then you can see all uppercase has been replaced with XX up, followed by the word. So there's some of those rules in action. You can also see multiple spaces have been replaced, with making it standard tokens. So that's the word tokenizer. The really interesting one is the subword tokenizer. Why would you need a subword tokenizer? Well, consider, for example, this sentence here. 我的名字是郝杰瑞. So this is, my name is Jeremy. But the interesting thing about it is there's no spaces here, right? That's because there are no spaces in Chinese, and there isn't really a great sense of what a word is in Chinese. In this particular sentence, it's fairly clear what the words are, but it's not always obvious. Sometimes the words are actually split, so some of it's at the start of a sentence and some of it's at the end. So you can't really do word tokenization for something like Chinese. So instead we use subword tokenization, which is where we look at a corpus of documents and we find the most commonly occurring groups of letters. And those commonly occurring groups of letters become the vocab. So for example, we would probably find 我的 would appear often because that means my, and 名字, oopsie daisy, and then 名字, for example, is name, and this is my westernized version of a Chinese name, which wouldn't be very common at all, so they would probably appear separately. So let's look at an example. Let's grab the first 2,000 movie reviews. Let's create the default subword tokenizer, which currently uses something called sentence piece. That might change. And now we're going to use something special, something very important, which is called setup. Transforms in fast.ai, you can always call this special thing called setup. It often doesn't do anything, but it's always there. But some transforms, like a subword tokenizer, actually need to be set up before you can use them. In other words, you can't tokenize into subwords until you know what the most commonly occurring groups of letters are. So passing a list of texts, and here's this list of texts, to setup will train the subword tokenizer. It'll find those commonly occurring groups of letters. So having done that, we can then, this is just for experimenting, we're going to pass in some size. We'll say what vocab size we want for our subword tokenizer. We'll set it up with our texts, and then we will have a look at a particular sentence. So for example, if we create a subword tokenizer with 1,000 tokens, and it returns this this tokenized string. Now this kind of long underscore thing is what we replace space with, because now we're using subword tokens. We kind of want to know where the sentences actually start and stop. Okay, and you can see here a lot of words are common enough sequences of letters that they get their own vocab item, whereas discovered wasn't common enough, so that became dis over ed, right? Video appears enough, whereas store didn't, so that became st or e. So you get the idea, right? So if we wanted a smaller vocab size, that would, as you see, even this doesn't become its own word. Movie is so common that it is its own word. So just becomes j, a, s, t, for example.
We have a question.
Okay.
How can we determine if the given pre-trained model, in this case Wikitext 103, is suitable enough for our downstream task? If we have limited vocab overlap, should we need to add an additional data set to create a language model from scratch?
If it's in the same language, so if you're doing English, it's almost always sufficient to use Wikipedia. We've played around with this a lot, and it was one of the key things that Sebastian Ruder and I found when we created the ULM Fit paper. Was before that time, people really thought you needed corpus-specific pre-trained models, but we discovered you don't, just like you don't that often need corpus-specific pre-trained vision models. ImageNet works surprisingly well across a lot of different domains. So Wikipedia has a lot of words in it. It would be really, I haven't come across an English corpus that didn't have a very high level of overlap with Wikipedia. On the other hand, if you're doing ULM Fit with like genomic sequences or Greek or whatever, then obviously you're going to need a different pre-trained model. So once we go up to a 10,000 word vocab, as you can see, basically every word, at least common word, becomes its own vocab item in the subword vocab, except say discovered, which becomes discover ed. So my guess is that subword approaches are going to become kind of the most common. Maybe they will be by the time you watch this. We've got some fiddling to do to get this working super well for fine-tuning. But I think I know what we have to do, so hopefully we'll get it done pretty soon. All right. So After we split it into tokens, the next thing to do is numericalization. So let's go back to our word tokenized text, which looked like this. And in order to numericalize, we will first need to call setup. So to save a bit of time, let's create a subset of our text. We'll just create a couple of hundred of the corpuses. Sorry, a couple of hundred of the reviews. So here's an example of one. And we'll create our numericalize object, and we'll call setup, and that's the thing that's going to create the vocab for us. And so after that, we can now take a look at the vocab. This is col repr is showing us a representation of a collection. It's what the L class uses underneath. And you can see when we do this that the vocab starts with the special tokens, and then we start getting the English tokens in order of frequency. So the default is a vocab size of 60,000. So that'll be the size of your embedding matrix by default. And if there are more than 60,000 unique words in your vocab, in your corpus, then the least common ones will be replaced with a special XX unknown token. So that'll help us avoid having a too big embedding matrix. All right, so now we can treat the numericalize object which we created as if it was a function, as we so often do in both fast.ai and PyTorch. And when we do, it'll replace each of our words with numbers. So 2, for example, is 0, 1, 2, beginning of string, beginning of stream. 8, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so a capitalized letter. There they are, XXBOS, XXMAG, etc. Okay? And then we can convert them back by indexing into the vocab and get back what we started with. Okay? Right. So now we have done the tokenization, we've done the numericalization, and so the next thing we need to do is to create batches. So let's say this is the text that we want to create batches from. And so if we tokenize that text, it'll convert it into this. And so let's take that and write it out here. Let's do it here. Let's take that and write it out here. So XXBOS, XXMAG in this chapter, XXBOS, XXMAG in this chapter. We will go back over the example of classifying, and then next row starts here. Movie reviews we studied in chapter 1, and dig deeper under the surface, full stop, XXMAG. First we will look at the etc. Okay, so we've taken these 90 tokens, and to create a batch size of 6, we've broken up the text into 6 contiguous parts, each of length 15. So 1, 2, 3, 4, 5, 6, and then we have 15 columns. Okay, so 6 by 15. Now ideally, we would just provide that to our model as a batch. And if indeed that was all the data we had, we could just pass it in as a batch. But that's not going to work for IMDb, because IMDb, once we concatenate all the reviews together, and then let's say we want to use a batch size of 64, then we're going to have 64 rows, and probably there's a few million tokens of IMDb, so a few million divided by 64 across, it's going to be way too big to fit in our GPU. So what we're going to do then is we're going to split up that big wide array, and we're going to split it up horizontally. So we'll start with XXBOS, XXMAG in this chapter, and then down here we will go back over the example of classifying. Movie reviews we studied in chapter 1 and dig deeper, under the surface, etc. So this would become our first mini batch. right? And so you can see what's happened is the kind of second row, right, actually is continuing what was like way down here. And so we basically treated each row as totally independent. So when we predict the second from the second mini batch, the second mini batch is going to follow from the first, and that each row, so row 1 in the second mini batch will join up to row 1 of the first. Row 2 of the second mini batch will join up to row 2 of the first. So please look at this example super carefully, because we found that this is something that every year a lot of students get confused about, because it's just not what they expected to see happen, right? So go back over this and make sure you understand what's happening in this little example. So that's what our mini batches are going to be. So the good news is that all these fiddly steps you don't have to do yourself. You can just use the language model data loader, or LM data loader. So if we take those all the tokens from the first 200 movie reviews and map them through our numericalized object, right? So now we've got numericalized versions of all those tokens, and then pass them into LM data loader, and then grab the first item from the data loader. Then we have 64 by 72. Why is that? Well, 64 is the default batch size, and 72 is the default sequence length. You see here we've got 1, 2, 3, 4, 5. Here we used a sequence length of 5, right? So what we do in practice is we use a default sequence length of 72. So if we grab the first of our independent variables and grab the first few tokens and look them up in the vocab, here it is, this movie which I just something at the video store, so that's interesting. So this was not common enough to be in our vocab, has apparently set around for And then if we look at the exact same thing but for the dependent variable, rather than being xxbos xxmaj this movie, it's xxmaj this movie. So you can see it's offset by 1, which means the end, rather than being around for it's for a couple. So this is exactly what we want. This is offset by 1 from here. So that's looking good. So we can now go ahead and use these ideas to try and build our even better IMDb sentiment analysis. And the first step will be to, as we discussed, create the language model. But let's just go ahead and use the fast.ai built-in stuff to do it for us, rather than doing all that messing around manually. So we can just create a data block. And our blocks are, it's going to be a text block from folder. And the items are going to be text files from these folders. And we're going to split things randomly, and then going to turn that into data loaders with a batch size of 128 and a sequence length of 80. In this case, our blocks, we're not just passing in a class directly, but we're actually passing in here a class method. And that's so that we can allow the tokenization, for example, to be saved, to be cached in some path, so that the next time we run this, it won't have to do it all from scratch. So that's why we have a slightly different syntax here. So once we've run this, we can call show batch. And so you can see here, we've got, for example, what xxmaj I've read, xxmaj death, blah, blah, blah. And you can see, so that's the independent variable. And so the dependent variable is the same thing offset by 1. So we don't have the what anymore, but it just goes straight to xxmaj I've read. And then at the end, this was also this. And of course, in the dependent variable, also this is. So this is that offset by 1, just like we were hoping for. Show batch is automatically denumericalizing it for us, turning it back into strings. But if we look at the actual, or you should look at the actual X and Y to confirm that you actually see numbers there. That'll be a good exercise for you, is to make sure that you can actually grab a mini batch from DL's LM. So now that we've got the data loaders, we can fine-tune our language model. So fine-tuning the language model means we're going to create a learner which is going to learn to predict the next word of a movie review. So that's our data, the data loaders for the language model. This is the pre-trained model. It's something called AWD LSTM, which we'll see how to create from scratch in a moment, or something similar to it. Dropout we'll learn about later. We see how much dropout to use. This is how much regularization we want. And what metrics do we want? We know about accuracy. Perplexity is not particularly interesting, so I won't discuss it, but feel free to look it up if you're interested. And let's train with FP16 to use less memory on the GPU, and for any modern GPU, it'll also run 2 or 3 times faster. So this grey bit here has been done for us, the pre-training of the language model for Wikitext 103. And now we're up to this bit, which is fine-tuning the language model for IMDb. So let's do one epoch. And as per usual, using a pre-trained model automatically calls freeze. So we don't have to freeze. So this is going to just actually train only the new embeddings initially. And we get an accuracy after 10 minutes or so of 30%. So that's pretty cool. So about a bit under a third of the time, our model is predicting the next word of a string. So I think that's pretty cool. Now, since this takes quite a while for each epoch, we may as well save it. And you can save it under any name you want, and that's going to put it into your learner's path into a model subfolder, and it'll give it a .pth extension for PyTorch. And then later on you can load that with learn.load after you create the learner. And so then we can unfreeze, and we can train a few more epochs, and we eventually get up to an accuracy of 34%. So that's pretty great. So once we've done all that, we can save the model, but actually all we really need to do is to save the encoder. What's the encoder? The encoder is all of the model except for the final layer. Oh, and we're getting a thunderstorm here. That could be interesting. We've never done a lesson with a thunderstorm before, but that's the joy of teaching during COVID-19. You get all the sound effects. So yeah, the final layer of our language model is the bit that actually picks a particular word out, which we don't need. So when we say save encoder, it saves everything except for that final layer. And that's the pre-trained model we're going to use. That is a pre-trained model of a language model that is fine-tuned from Wikipedia, fine-tuned using IMDb, and doesn't contain the very last layer. Rachel, any questions at this point?
Do any language models attempt to provide meaning? For instance, I'm going to the store is the opposite of I'm not going to the store. Or I barely understand this stuff and that ball came so close to my ear I heard it whistle. Both contain the idea of something almost happening, being right on the border. Is there a way to indicate this kind of subtlety in a language model?
Yeah, absolutely. Our language model will have all of that in it, or hopefully it will. Hopefully it'll learn about it. We don't have to program that. The whole point of machine learning is it learns it for itself. But when it sees a sentence like, hey, careful, that ball nearly hit me, the expectation of what word is going to happen next is going to be different to the sentence, hey, that ball hit me. So yeah, language models generally you see in practice tend to get really good at understanding all of these nuances of English or whatever language it's learning about. Okay, so we have a fine-tuned language model. So the next thing we're going to do is we're going to try fine-tuning a classifier. But before we do, just for fun, let's look at text generation. We can write ourselves some words like I liked this movie because, and then we can create, say, 2 sentences, each containing, say, 40 words. And so we can just go through those 2 sentences and call learn.predict passing in this text and asking to predict this number of words with this amount of kind of randomization, and see what it comes up with. I liked this movie because of its story and characters. The storyline was very strong, very good for a sci-fi. The main character, Alucard, was very well developed and brought the whole story, blah, blah, blah. Second attempt. I liked this movie because I like the idea of the premise of the movie, the very convenient virus, which, well, when you have to kill a few people, the evil machine has to be used to protect, blah, blah, blah. So as you can see, it's done a good job of inventing language. There are much, well, I shouldn't say more sophisticated. There are more careful ways to do generation from a language model. This learn.predict uses the most kind of basic possible one. But even with a very simple approach, you can see we can get from a fine-tuned model some pretty authentic looking text. And so in practice, this is really interesting because we can now, by using the prompt, you can kind of get it to generate, appropriate, context-appropriate text, particularly if you fine-tune from a particular corpus. Anyway, that was really just a little demonstration of something we accidentally created on the way. Of course, the whole purpose of this is actually just to be a pre-trained model for classification. So to do that, we're going to need to create another data block. And this time we've got 2 blocks, not 1. We've got a text block again, just like before. But this time we're going to ask fast.ai not to create a vocab from the unique words, but use the vocab that we already have from the language model. Because otherwise, obviously, there's no point reusing a pre-trained model if the vocab's different. The numbers would mean totally different things. So that's the independent variable, and the dependent variable, just like we've used before, is a category. So a category block is for that. As we've used many times, we're going to use parent label to create our dependent variable. That's a function. Get items, we'll use get text files, just like before. And we'll split using grandparent splitter as we've used before for vision. So this has been used for vision. This has been used for vision. And then we'll create our data loaders with a batch size of 128, a sequence length of 72. And now show batch. Here we can see an example of subset of a movie review and a category. Yes, question.
Do the tokenizers use any tokenization techniques like stemming or lemmatization, or is that an outdated approach?
That would not be a tokenization approach. So stemming is something that actually removes the stem, and we absolutely don't want to do that. That is certainly an outdated approach. In English, we have stems for a reason. They tell us something. So we don't like to remove anything that can give us some kind of information. We used to use that for kind of pre-deep learning NLP quite a bit because we didn't really have good ways like embedding matrices of handling big vocabs that just differed in the kind of the end of a word. But nowadays we definitely don't want to do that. One other difference here is previously we had an is lm equals true when we said text block from folder to say it was a language model. We don't have that anymore because it's not a language model. Okay, now one thing with a language model that was a bit easier was that we could concatenate all the documents together, and then we could split them by batch size to create, well, not split them by batch size, split them into a number of substrings based on the batch size. And that way we could ensure that every mini batch was the same size. It would be batch size by sequence length. But for classification, we can't do that. We actually need each dependent variable label to be associated with each complete movie review. Now, we're not showing the whole movie review here. We've truncated it just for display purposes, but we're going to use the whole movie review to make our prediction. Now, the problem is that if we're using a batch size of 128, and our movie reviews are often like 3,000 words long, we could end up with something that's way too big to fit into the GPU memory. So how are we going to deal with that? Well, again, we can split them up. So first of all, let's grab a few of the movie reviews just for a demo here and numericalize them. And if we have a look at the length, so map the length over each, you can see that they do vary a lot in length. Now we can split them into sequences, and indeed we have asked to do that, sequence length 72. But when we do so, we don't even have the same number of subsequences when we split each of these into 72 long sections. They're going to be all different lengths. So how do we deal with that? Well, just like in Vision, we can handle different sized sequences by adding padding. So we're going to add a special XXPad token to every sequence in a mini batch. So like in this case, it looks like 581 is the longest. So we would add enough padding tokens to make this 581 and this 581 and this 581 and so forth. And then we can split them into sequence len, into 72 long, in the mini batches, and we'll be right to go. Now, obviously, if your lengths are very different like this, adding a whole lot of padding is going to be super wasteful. So another thing that fast.ai does internally is it tries to shuffle the documents around so that similar length documents are in the same mini batch. It also randomizes them, but it kind of approximately sorts them, so it wastes a lot less time on padding. Okay, so that is what happens when we don't have to do any of that manually. When we call text block from folder without the isLm, it does all that for us. And then we can now go ahead and create a learner. This time it's going to be a text classifier learner. Again, we're going to base it off AWD LSTM. Pass in the data loaders we just created. For metric, we'll just use accuracy, make it FP16 again. And now we don't want to use a pre-trained Wikipedia model. In fact, there is no pre-trained Wikipedia classifier because, what you classify matters a lot. So instead, we load the encoder. So remember everything except the last layer, which we saved just before. So we're going to load as our pre-trained model a language model for predicting the next word of a movie review. So let's go ahead and fit one cycle. And again, by default, it will be frozen. So it's only the final layer, which is the randomly added classifier layer, that's going to be trained. It took 30 seconds. And look at this, we already have 93%. So that's pretty similar to what we got back in lesson 1, but rather than taking about 12 minutes, once all the pre-training's been done, it takes about 30 seconds. So this is quite cool. You can create a language model for your kind of general area of interest, and then you can create all kinds of different classifiers pretty quickly. And so that's just looking at the fine-tuning the final randomly added layer. So now we could just unfreeze and keep learning. But something we found is for NLP, it's actually better to only unfreeze one layer at a time, not to unfreeze the whole model. So in this case, we've automatically unfrozen the last layer. And so then to unfreeze the last couple of layer groups, we can say freeze 2 minus 2, and then train a little bit more. And look at this, we're already beating, after a bit over a minute, easily beating what we got in lesson 1. And then freeze 2 minus 3 to unfreeze another few layers. Now we're up to 94. And then finally unfreeze the whole model, and we're up to about 94.3% accuracy. And that was literally the state of the art for this very heavily studied data set just 3 years ago. If you also reverse all of the reviews to make them go backwards and train a second model on the backwards version, and then average the predictions of those two models as an ensemble, you get to 95.1% accuracy. And that was the state of the art that we actually got in the ULM Fit paper. And it was only beaten for the first time a few months ago using a way, way bigger model, way more data, way more compute, and way more data augmentation. I should mention, actually, with the data augmentation, one of the cool things they did do was they actually figured out also a way to even beat our 95.1 with less data as well. So I should mention that, actually. The data augmentation has become a really, since we created the ULM fit paper, has become a really, really important approach. Any questions, Rachel?
Can someone explain how a model trained to predict the last word in a sentence can generalize to classify sentiment? They seem like different domains.
Yeah, that's a great question. They're very different domains, and it's really amazing. And basically the trick is that to be able to predict the next word of a sentence, you just have to know a lot of stuff about not only the language, but about the world. So if, let's say we wanted to finish the next word of this sentence. By training a model on all the text read backwards and averaging the predictions of these two models, we can even get to 95.1% accuracy, which was the state-of-the-art introduced by the what? So to be able to fill in the word ULM fit, you would have to know a whole lot of stuff about the fact that there's a thing called fine-tune, pre-trained language models, and which one gets which results, and that ULM fit got this particular result. I mean, that would be an amazing language model that could fill that in correctly. I'm not sure that any language models can, but to give you a sense of like what you have to be able to do to be good at language modeling. So if you're going to be able to predict the next word of a sentence like, wow, I really love this movie. I love every movie containing Meg what, right? Maybe it's Ryan. You would have to know about like the fact that Meg Ryan is an actress and actresses are in movies and so forth. So when you know so much about English and about the world, to then turn that into something which recognizes that I really love this movie is a good thing rather than a bad thing is just not a very big step. And as we saw, you can actually get that far using just fine-tuning just the very last layer or two. So it's amazing. And I think that's super, super cool.
All right, another question. How would you do data augmentation on text?
Well, you would probably Google for unsupervised data augmentation and read this paper and things that have cited it. So this was the one that easily beat our IMDb result with only 20 labeled examples, which is amazing, right? And so they did things like, if I remember correctly, translate every sentence into a different language and then translate it back again. So you kind of get like different rewordings of the sentence that way. So kind of tricks like that. Now, let's go back to the generation thing. So remember we saw that we can generate context-appropriate sentences. And it's important to think about what that means in practice. When you can generate context-appropriate sentences, have a look, for example, at even before this technology existed in 2017. The FCC asked for comments about a proposal to repeal net neutrality. And it turned out that less than 800,000 of the 22 million comments actually appeared to be unique. And this particular person, Jeff Cow, discovered that a lot of the submissions were slightly different to each other by kind of like picking up different, the green bit would either be citizens or people like me or Americans. And the red bit would be as opposed to or rather than and so forth. So like, and that made a big difference to, I believe, to American policy. Here's an example of a Reddit conversation. You're wrong. The defense budget is a good example of how badly the US spends money on the military, ... So Somebody else, yeah, but that's already happening. There's a huge increase in the military budget. I didn't mean to sound like stop paying for the military. I'm not saying that we cannot pay the bills. Well, all of these are actually created by a language model called GPT-2. And this is a very concerning thing around disinformation, is that never mind fake news, never mind deep fakes. Think about like what would happen if somebody invested a few $1 million in creating a million Twitter bots and Facebook groups bots and Weibo bots, and made it so that 99% of the content on social networks were deep learning bots. And furthermore, they were trained not just to optimize the next word of a sentence, but were trained to optimize the level of disharmony created, or the level of agreeableness for half of them and disagreeableness for the other half of them. You could create like a whole lot of just awful toxic discussion, which is actually the goal of a lot of propaganda outfits. It's not so much to push a particular point of view, but to make people feel like there's no point engaging because the truth is too hard to understand, or whatever. So Rachel and I are both super worried about what could happen to discourse now that we have this incredibly powerful tool, and I'm not even sure we don't have a great sense of what to do about it. Algorithms are unlikely to save us here. If you could create a classifier which could do a good job of figuring out whether something was generated by a algorithm or not, then I could just use your classifier as part of my training loop to train an algorithm that can actually learn to trick your classifier. So this is a real worry, and the only solutions I've seen are those which are kind of based on cryptographic signatures, which is another whole can of worms, which has never really been properly sorted out, at least not in the Western world in a privacy-centric way. All right, so yes.
Just on that note, I'll add, and I'll link to this on the forums. I gave a keynote at SciPy conference last summer, which is the Scientific Python conference, and went into a lot more detail about the threat that Jeremy's describing about using advanced language models to manipulate public opinion. And so if you want to kind of learn more about the dangers there and exactly what that threat is, you can find that in my SciPy keynote.
Great. Thanks so much, Rachel. So let's have a 5-minute break, and see you back here in 5 minutes. So we're going to finish with a kind of a segue into what will eventually be part 2 of the course, which is to go right underneath the hood and see exactly how a more complex architecture works. And specifically, we're going to see how a recurrent neural network works. Do we have a question first?
In the previous lesson MNIST example, you showed us that under the hood, the model was learning parts of the image, like curves of a 3 or angles of a 7. Is there a way to look under the hood of the language models to see if they are learning rules of grammar and syntax? Would it be a good idea to fine-tune models with examples of domain-specific syntax, like technical manuals, or does that miss the point of having the model learn for themselves?
Yeah, there are tools that allow you to kind of see what's going on inside an NLP model. We're not going to look at them in this part of the course. Maybe we will in part 2, but certainly worth doing some research to see what you can find. And there's certainly PyTorch libraries you can download and play with. Yeah, I mean, I think it's a perfectly good idea to incorporate some kind of technical manuals and stuff into your training corpus. There's actually been some recent papers on this general idea of trying to kind of create some carefully curated sentences as part of your training corpus. It's unlikely to hurt, and it could well help. All right, so let's have a look at RNNs. Now, when Sylvain and I started creating the RNN stuff for fast.ai, the first thing I did actually was to create a new dataset. And the reason for that is I didn't find any datasets that would allow for quick prototyping and really easy debugging. So I made one, which we call human numbers, and it contains the first 10,000 numbers written out in English. And I am surprised at how few people create datasets. I create datasets frequently. I specifically look for things that can be kind of small, easy to prototype, good for debugging and quickly trying things out. And very, very few people do this, even though like this human numbers dataset, which has been so useful for us, took me, I don't know, an hour or two to create. So this is definitely an underappreciated, underutilized technique. So we can grab the human numbers dataset and we can see that there's a training and a validation text file. We can open each of them. And for now, we're just going to concatenate the two together into a file called lines. And you can see that the contents are 1, 2, 3, etc. And so there's a new line at the end of each. We can concatenate those all together and put a full stop between them as so. Okay, and then you could tokenize that by splitting on spaces. And so, for example, here's tokens 100 to 110, new number 42, new number 43, new number 44, and so forth. So you can see I'm just using plain Python here. There's not even any PyTorch, certainly not any fast.ai. To create a vocab, we can just create all the unique tokens, of which there are 30. And then to create a lookup from, so that's a lookup from a word to an ID, from an ID to a word. To go from a word to an ID, we can just enumerate that and create a dictionary from word to ID. So then we can numericalize our tokens by calling word to index on each one. And so here's our tokens. And here's the equivalent numericalized version. So you can see on fairly small data sets when we don't have to worry about scale and speed and the details of tokenization in English. You can do the whole thing in just plain Python. The only other thing we did to save a little bit of time was use L, but you could easily do that with the Python standard library in about the same amount of code. So hopefully that gives you a good sense of really what's going on with tokenization and numericalization, all done by hand. So let's create a language model. So one way to create a language model would be to go through all of our tokens, and let's create a range from 0 to the length of our tokens minus 4 and every 3 of them. And so that's going to allow us to grab 3 tokens at a time. 1.2.3. 4.5.6.7.8 and so forth, right? So here's the first 3 tokens, and then here's the 4th token, and here's the second 3 tokens, and here's the 7th token, and so forth. So these are going to be our independent variables, and this will be our dependent variable. So here's a super kind of naive, simple language model data set for our human numbers question. So we can do exactly the same thing as before, but use the numericalized version and create tensors. So this is exactly the same thing as before, but now through numericalized and as tensors. And we can create a data loaders object from data sets. And remember, these are data sets because they have a length and we can index into them. Right? And so we can just grab the first 80% of the tokens as the training set, the last 20% as the validation set, like so. Batch size 64, and we're ready to go. So we really used very, very little I mean, the only PyTorch we used was to create these tensors, and the only fast.ai we used was to create the data loaders, and it's just grabbing directly from the data sets, so it's really not doing anything clever at all. So let's see if we can now create a neural network architecture which takes 3 numericalized words at a time as input and tries to predict the 4th as dependent variable. So here is just such a language model. It's a 3-layer neural network. So we've got a linear layer here, which we're going to use once, twice, 3 times. And after each of them, we call ReLU, as per usual. But there's a little bit more going on. The first interesting thing is that rather than each of these being a different linear layer, we've just created one linear layer here, which we've reused, as you can see, 1, 2, 3 times. So that's the first thing that's a bit tricky. And so there's a few things going on which are a little bit different to usual, but the basic idea is here. We've created an embedding, an NN linear, another NN linear, and then here we've used the linear layers and ReLU. So it's very nearly a totally standard 3-layer neural net. I guess 4 really, because there's an output layer. Yes, Rachel?
We have a question.
Sure.
Is there a way to speed up fine-tuning the NLP model? 10 plus minutes per epoch slows down the iterative process quite a bit. Any best practices or tips?
I can't think of any, obviously, other than to say you don't normally need to fine-tune it that often. The work is often more at the classifier stage. So, yeah, I tend to kind of just leave it running overnight or while I have lunch or something like that. Yeah, just make sure you don't sit there watching it. Go and do something else. This is where it can be quite handy to have a second GPU or fire up a second AWS instance or whatever, so you can kind of keep moving while something's training in the background. All right, so what's going on here in this model? To describe it, we're actually going to develop a little kind of pictorial representation. And the pictorial representation is going to work like this. Let's start with a simple linear model to define this pictorial representation. A simple linear model has an input of size, batch size by number of inputs. And so we're going to use a rectangle to represent an input. We're going to use an arrow to represent a layer computation. So in this case, there's going to be a matrix product for a simple linear model. There'd be a matrix. Actually, sorry, this is a single hidden layer model. There'll be a matrix product followed by a ReLU. So that's what this arrow represents. And out of that, we're going to get some activations. And so circles represent computed activations. And it would be, we call this a hidden layer. It would be of size batch size by number of activations. That's its size. And then to create a neural net, we're going to do a second matrix product, and this time a softmax. So the computation, again, represented by the arrow. And then output activations are a triangle. So the output would be batch size by num classes. So let me show you the pictorial version of this. So this is going to be our legend. Triangle is output, circle hidden, rectangle input. And here it is. We're going to take the first word as an input. It's going to go through a linear layer and a ReLU. And you'll notice here I've deleted the details of what the operations are at this point, and I've also deleted the sizes. So every arrow is basically just a linear layer followed by a nonlinearity. So we take the word 1 input and we put it through the layer, the linear layer and the nonlinearity to give us some activations. So there's our first set of activations. And when we put that through another linear layer and nonlinearity, to get some more activations. And at this point we get word 2. And word 2 is now goes through a linear layer and a nonlinearity. And these two, when two arrows together come to a circle, it means that we add or concatenate, either's fine, the two sets of activations. So we'll add the set of activations from this input to the set of activations from here to create a new set of activations. And then we'll put that through another linear layer and a ReLU. And again, word 3 is now going to come in and go through a linear layer and a ReLU, and they'll get added to create another set of activations. And then they'll go through a final linear layer and ReLU I guess softmax to create our output activations. So this is our model. It's basically a standard 1, 2, 3, 4 layer model. But a couple of interesting things are going on. The first is that we have inputs coming in to later layers and get added. So that's something we haven't seen before. And the second is all of the arrows that are the same color use the same weight matrix. So every time we get an input, we're going to put it through a particular weight matrix. And every time we go from one set of activations to the next, we'll put it through a different weight matrix. And then to go from the activations to the output, we'll use a different weight matrix. So if we now go back to the code, to go from input to hidden, not surprisingly, we always use an embedding. So in other words, an embedding is the green. Okay, and you'll see we just create one embedding, and here is the first, so here's X, which is the 3 words. So here's the first word, X0, and it goes through that embedding. And word 2 goes through the same embedding, and word 3, index number 2, goes through the same embedding. And then each time you say we add it to the current set of activations. And so having got the embedding, we then put it through this linear layer. And again, we get the embedding, add it to the activations, and put it through the linear layer. And again, same thing here, put it through the same linear layer. So HH is the orange. So these set of activations we call the hidden state. Okay, and so the hidden state is why it's called H. And so if you follow through these steps, you'll see how each of them corresponds to a step in this diagram. And then finally at the end, we go from the hidden state to the output, which is this linear layer, hidden state to the output. Okay. And then we don't have the actual softmax there because, as you'll remember, we can incorporate that directly into the loss function, the cross-entropy loss function, using PyTorch. So one nice thing about this is everything we're using we have previously created from scratch. So there's nothing magic here. We've created our own embedding layer from scratch. We've created our own linear layer from scratch. We've created our own ReLU from scratch. We've created our own cross-entropy loss from scratch. So you could actually try building this whole thing yourself from scratch. So why do we, just in terms of the nomenclature, IH, so H refers to hidden. So this is a layer that goes from input to hidden. This is one that goes from hidden to hidden. This is one that goes from hidden to output. So if any of this is feeling confusing at any point, go back to where we actually created each one of these things from scratch and create it from scratch again. Make sure you actually write the code so that nothing here is mysterious. So why do we use the same embedding matrix each time we have a new input word for input word index 0, 1, and 2? Well, because conceptually, they all represent English words for human numbers. So why would you expect them to be a different embedding? They all should have the same representation because they all have the same meaning. Same for this hidden to hidden. At each time, we're basically describing how to go from one token to the next of our language model. So we'd expect it to be the same computation. So that's basically what's going on here. So having created that model, we can go ahead and instantiate it. So we're going to have to pass in the vocab size for the embedding, and the number of hidden, right? So that's the number of activations. So here we create the model, and then we create a learner by passing in a model and our data loaders and a loss function and optionally metrics, and we can fit. Now, of course, this is not pre-trained, right? This is not an application-specific learner, so it wouldn't know what pre-trained model to use. So this is all random. And we're getting somewhere around 45 to 50% or so accuracy. Is that any good? Well, you should always compare to random, or not random. You should always compare to like the simplest model, where the simplest model is like some average or something. So what I did is I grabbed the validation set, so all the tokens, put it into a Python standard library counter, which simply counts how many times each thing appears. I found that the word 1,000 is the most common. And then I said, okay, what if we used 7,104, 1,000, that's here, and divide that by the length of the tokens, and we get 15%, which in other words means if we always just predicted, I think the next word will be 1,000, we would get 15% accuracy. But in this model, we got around 45 to 50% accuracy. So in other words, our model is a lot better than the simplest possible baseline. So we've learned something useful. That's great. So the first thing we're going to do is we're going to refactor this code. Because you can see we've got X going into IH, going into HH, going into ReLU. X going into IH, going into HH, going to ReLU. X going into IH, going into HH, going to ReLU. How would you refactor that in Python? You would, of course, use a for loop. So let's go ahead and write that again. So these lines of code are identical. In fact, these lines of code are identical, as is this. And we're going to, instead of doing all that stuff manually, we create a loop that goes through 3 times. And in each time it goes IH, add to our hidden, HH, ReLU. And then at the end, hidden to output. So this is exactly the same thing as before, but it's just refactored with a for loop. And we can train it again, and again we get the same, basically 45 to 50%, as you would expect, because it's exactly the same. It's just been refactored. So here's something crazy. This is a recurrent neural network. Even though it's like exactly the same as this, right? It's just been refactored into a loop. And so, believe it or not, that's actually all an RNN is. An RNN is a simple refactoring of that model, with that deep learning linear model we saw. I shouldn't say linear model. Deep learning model of simple linear layers with ReLUs. So let's draw our pictorial representation again. So remember, this was our previous pictorial representation. We can refactor the picture as well. So instead of showing these dots separately, we can just take this arrow and represented it as a loop. Because that's all that's happening, right? So the word 1 goes through an embedding, goes into this activations, which then just gets repeated from 2 to the n, 2 to n minus 1, where n at this time is, we've got 3 words basically, for each word coming in as well. And so we've just refactored our diagram, and then eventually it goes through our blue to create the output. So this diagram is exactly the same as this diagram, just replacing the middle with that loop. So that's a recurrent neural net. And so H, remember, was something that we just kept track of here, H, as we added each layer to it. And here, we just have it inside the loop. We initialize it as 0, which is kind of tricky. And the reason we can do that is that 0 plus a tensor will broadcast this 0. So that's a little neat feature. That's why we don't have to make this a particular size tensor to start with. Okay, so we're going to be seeing the word hidden state a lot. And so it's important to remember that hidden state simply represents these activations that are occurring inside our recurrent neural net. And a recurrent neural net is just a refactoring of a particular kind of fully connected deep model. So that's it. That's what an RNN is. No questions at this point, Rachel? Something that's a bit weird about it, though, is that for every batch, we're setting our hidden state to 0. Even although we're going through the entire set of numbers, the human numbers data set, in order. So you would think that by the time you've gone like 1, 2, 3, you shouldn't then forget everything we've learnt when you go to 4, 5, 6, right? It would be great to actually remember where we're up to and not reset the hidden state back to 0 every time. So we can absolutely do that. We can maintain the state of our RNN. And here's how we would do that. Rather than having something called h, we'll call it self.h. And we'll set it to 0 at the start when we first create our model. Everything else here is the same. And everything else here is the same. And then there's just one extra line of code here. What's going on here? Well, here's the thing. If h is something which persists from batch to batch, then effectively this loop is effectively kind of becoming infinitely long, right? Our deep learning model, therefore, is getting effectively, well, not infinitely deep, but as deep as the entire size of our data set, because every time we're stacking new layers on top of the previous layers. The reason this matters is that when we then do backpropagation, when we then calculate the gradients, we're going to have to calculate the gradients all the way back through every layer, going all the way. So by the time we get to the end of the data set, we're going to be effectively backpropagating not just through this loop, but remember self.h was created also by the previous quarter forward and the previous quarter forward and the previous quarter forward. So we're going to have this incredibly slow calculation of the gradients all the way back to the start. It's also going to use up a whole lot of memory because it's going to have to store all those intermediate gradients in order to calculate them. So that's a problem. And so the problem is easily solved by saying detach. And what detach does is it basically says throw away my gradient history. Forget that I was calculated from some other gradients. So the activations are still stored, but the gradient history is no longer stored. And so this kind of cuts off the gradient computation. And so this is called truncated backpropagation. So exactly the same lines of code as the other two models. H equals 0 has been moved into self.h equals 0. These lines of code are identical, and we've added one more line of code. So the only other thing is that from time to time, we might have to reset self.h to 0. So I've created a method for that, and we'll see how that works shortly. Okay, so backpropagation, oh sorry, I was using the wrong jargon. Backpropagation through time is what we call it when we calculate the backprop over going back through this loop. All right, now we do need to make sure that the samples are seen in the correct order, you know, given that we need to make sure that every batch connects up to the previous batch. So go back to notebook 10 to remind yourself of what that needs to look like. But basically the first batch, we see that the length of our sequences divided by the batch size is 328. So the first batch will be index number 0, then m, then 2 times m, and so forth. And the second batch will be 1, m plus 1, 2 times m plus 1, and so forth. So the details don't matter, but here's how we create, do that indexing. So now we can go ahead and call that group chunks function to create our training set and our validation set. And certainly don't shuffle, because that would break everything in terms of the ordering. And then there's one more thing we need to do, which is we need to make sure that at the start of each epoch, we call reset. Because at the start of the epoch, we're going back to the start of our natural numbers. So we need to set self.h back to 0. So something that we'll learn about in part 2 is that fast.ai has something called callbacks. And callbacks are classes which allow you to basically say, during the training loop, I want you to call some particular code. And in particular, this is going to call this code. And so you can see callbacks are very small, or can be very small. They're normally very small. When we start training, it'll call reset. When we start validation, it'll call reset. So this is each epoch. And when we're all finished fitting, it will call reset. And what does reset do? It does whatever you tell it to do. And we told it to be self.h equals 0. So if you want to use a callback, you can simply add it to the callbacks list, CBs, when you create your learner. And so now when we train, that's way better. Okay, so we've now actually kept, this is called a stateful RNN. It's actually keeping the state, keeping the hidden state from batch to batch. Now we've still got a bit of a obvious problem here, which is that if you look back to the data that we created, we used these first 3 tokens to predict the 4th, and then the next 3 tokens to predict the 7th, and then the next 3 tokens to predict the one after, and so forth. Effectively, what we'd rather do, you would think, is predict every word, not just every 4th word. It seems like we're throwing away a lot of signal here, which is pretty wasteful. So we want to create more signal. And so the way to do that would be, rather than putting this output stage outside the loop, right? So this dotted area is the bit that's looped. What if we put the output inside the loop? So in other words, after every hidden state was created, we immediately did a prediction. And so that way we could predict after every time step, and our dependent variable could be the entire sequence of numbers offset by 1. So that would give us a lot more signal. So we have to change our data so that the dependent variable has each of the next 3 words after each of the 3 inputs. So instead of being just the numbers from I to I plus SL as input, and then I plus SL plus 1 as output, we're going to have the entire set offset by 1 as our dependent variable. So and we can now do exactly the same as we did before to create our data loaders. And so you can now see that each sequence is exactly the previous, is the independent variable and the dependent variable are the same thing, but offset by 1. Okay. And then we need to modify our model very slightly. This code is all exactly the same as before. But rather than now returning one output, we'll create a list of outputs and we'll append to that list after every element of the loop. And then at the end, we'll stack them all up. And then this is the same. So it's nearly exactly the same. Okay, just a very minor change. Our loss function we need to create our own loss function, which is just the cross entropy loss. But we need to just flatten it out. So the target gets flattened out, the input gets flattened out. And so then we can now pass that as our loss function. Everything else here is the same, and we can fit. And we've gone from, I can't remember, 58 to 64. So it's improved a little bit. So that's good. You know, we did find this a little flaky. Sometimes it would train really well. Sometimes it wouldn't train great. But sometimes we often got this reasonably good answer. Now, one problem here is, although effectively we have quite a deep neural net, if you kind of go back to the version, so this version where we have the loop in it is kind of the normal way to think about an RNN, but perhaps an easier way to think about it is what we call the unrolled version. And the unrolled version is when you look at it like this. Now, if you unroll this stateful neural net we have, it is quite deep, but every single one of the hidden to hidden layers uses exactly the same weight matrix. So really, it's not really that deep at all, because it can't really do very sophisticated computation because it has to use the same weight matrix every time. So in some ways, it's not really any smarter than a plain linear model. So it would be nice to try to, create a truly deep model, have multiple different layers that it can go through. So we can actually do that easily enough by creating something called a multi-layer RNN. And all we do is we basically take that diagram we just saw before and we repeat it. But, and this is actually a bit unclear, the dotted arrows here are different weight matrices to the non-dotted arrows here. So we can have a different hidden to hidden weight matrix in the kind of second set of RNN layers, and a different weight matrix here for the second set. And so this is called a stacked RNN or a multi-layer RNN. And so here's the same thing in the unrolled version, right? So this is exactly the same thing, but showing you the unrolled version. Writing this out by hand, maybe that's quite a good exercise, or particularly this one would be quite a good exercise, but it's kind of tedious, so we're not going to bother. Instead, we're going to use PyTorch's RNN class. And so PyTorch's RNN class is basically doing exactly what we saw here, right? And specifically, this part here and this part here, right? But it's nice that it also has an extra number of layers parameter that lets you tell it how many to stack on top of each other. So it's important when you start using PyTorch's RNN to realize there's nothing magic going on, right? You're just using this refactored for loop that we've already seen. So we still need the input to hidden embedding. This is now the hidden to hidden with the loop all done for us. And then this is the hidden to output just as before. And then this is our hidden just like before. So now we don't need the loop. We can just call self.rnn and it does the whole loop for us. We can do all the input to hidden at once to save a little bit of time, because thanks to the wonder of embedding matrices. And as per usual, we have to go detach to avoid getting a super deep effective network, and then pass it through our output linear layer. So this is exactly the same as the previous model, except that we have just refactored it using nn.rnn, and we said we want more than one layer. So let's request, say, 2 layers. We still need the model resetter just like before, because remember, nothing's changed. And let's go ahead and fit. And, oh, it's terrible. So, why is it terrible? Well, the reason it's terrible is that now we really do have a very deep model. And very deep models are really hard to train because we can get exploding or disappearing activations. So what that means is we start out with some initial state, and we're gradually putting it through all of these layers and all of these layers, right? And so each time we're doing a matrix multiplication, which remember is just doing a whole bunch of multiplies and adds, and then we multiply and add, and we multiply and add, and we multiply and add, and we multiply and add. And if you do that enough times, you can end up with very, very, very big results. Or, so that would be if the kind of things we're multiplying and adding by are pretty big, or very, 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 very small results. Particularly because we're putting it through the same layer again and again, right? And why is that a problem? Well, if you multiply by 2 a few times, you get 1, 2, 4, 8, etc. And after 32 steps, you're already at 4 billion. Or if you start at 1 and you multiply by half a few times, after 32 steps, you're down at this tiny number. So a number even slightly higher or lower than 1 can kind of cause an explosion or disappearance of a number. And matrix multiplication is just multiplying numbers and adding them up. So exactly the same thing happens to matrix multiplication. You kind of have matrices that grow really big or grow really small. When that does that, you're also going to have exactly the same things happening to the gradients. They'll get really big and really small. And one of the problems here is that numbers are not stored precisely in a computer. They're stored using something called floating point. So we stole this nice diagram from this article called What You Never Wanted to Know About Floating Point, but will be forced to find out. And here we're at this point where we're forced to find out. And it's basically showing us the granularity with which numbers are stored. And so the numbers that are further away from 0 are stored much less precisely than the numbers that are close to 0. And so if you think about it, that means that the gradients further away from 0 could actually, for very big numbers, could actually become 0 themselves, because you could actually end up in kind of with 2 numbers that are between these kind of little gradations here. And you actually end up with the same thing with the really small numbers, because the really small numbers, although they're closer together, the numbers that they represent are also very close together. So in both cases, the kind of the relative accuracy gets worse and worse. So you really want to avoid this happening. There's a number of ways to avoid this happening. And this is the same for really deep convolutional neural nets or really deep kind of tabular, standard tabular networks. Anytime you have too many layers, it can become difficult to train, and you generally have to use like either really small learning rates, or you have to use special techniques that avoid exploding or disappearing activations or gradients. For RNNs, one of the most popular approaches to this is to use an architecture called an LSTM. And I am not going to go into the details of an LSTM from scratch today, but it's in the book and in the notebook. But the key thing to know about an LSTM is, let's have a look, is that rather than just being a matrix multiplication, it is this, which is that there are a number of linear layers that it goes through, and those linear layers are combined in particular ways. And the way they're combined, which is shown in this kind of diagram here, is that it basically is designed such that that there are like little mini neural networks inside the layer which decide how much of the previous state is kept, how much is thrown away, and how much of the new state is added. And by letting it have little neural nets to kind of calculate each of these things, it allows the LSTM layer, which again is shown here, to decide how much of an update to do at each time. And then with that capability, it basically allows it to avoid kind of updating too much or updating too little. And by the way, this code you can refactor, which Sylvain did here, into a much smaller amount of code, but these two things are exactly the same thing. So as I said, I'm not going to worry too much about the details of how this works now. The important thing just to know is that you can replace the matrix multiplication in an RNN with this sequence of matrix multiplications and sigmoids and times and plus. And when you do so, you will very significantly decrease the amount of gradient or activation, explosions or disappearances. So that's called an LSTM cell, and an RNN which uses this instead of a matrix multiplication is called an LSTM. And so you can replace nn.rnn with nn.lstm. Other than that, we haven't really changed anything, except that LSTMs, because they have more of these layers in them, we actually have to make our hidden state have more layers in as well. But other than that, we can just replace LSTM, RNN with LSTM, and we can call it just the same way as we did before. We can detach just like before, but that's now a list, so we have to detach all of them and pop it through our output layer, which is exactly as before. Reset is just as before, except it's got a loop through each one. And we can fit it in exactly the same way as before. And as you can see, we end up with a much better result, which is great.
We have two questions.
Okay, perfect.
Could we somehow use regularization to try to make the RNN parameters close to the identity matrix? Or would that cause bad results because the hidden layers want to deviate from the identity during training?
So we're actually about to look at regularization. So we will take a look. The identity matrix, for those that don't know or don't remember, is the matrix where if you multiply it by it, you get exactly the same thing that you started with. So just like if you multiply by 1, you get back the same number you started with. For linear algebra, if you multiply by the identity matrix, you get the same matrix you started with. And actually, one quite popular approach to initializing the hidden-to-hidden activations is to initialize with an identity matrix, which ensures that you start with something which doesn't have gradient explosions or activation explosions. There are, we're about to have a look at some more regularization approaches, so let's wait until we do that.
All right, next question. Is there a way to quickly check if the activations are disappearing / exploding?
Absolutely. Just go ahead and calculate them. And we'll be looking at that in a lot more detail in part 2. But a really great exercise would be to try to figure out how you can actually output the activations of each layer. And it would certainly be very easy to do that in the RNNs that we built ourselves from scratch, because we can actually see the linear layers. And so you could just print them out or print out some statistics or store them away or something like that. Fast.ai has a class called activation stats. Which kind of you can check out if you're interested. That's a really good way to specifically to do this. Okay, so regularization is important. We have potentially a lot of parameters and a lot of layers. It would be really nice if we can do the same kind of thing that we've done with our CNNs and so forth, which is to use more parameters, but then use regularization to ensure that we don't overfit. And so we can certainly do that with an LSTM as well. And perhaps the best way to do that is to use something called dropout. And dropout is not just used for RNNs. Dropout is used all over the place, but it works particularly well in RNNs. This is a picture from the dropout paper. And what happens in dropout is here's a kind of a picture of three fully connected layers. No, sorry, I guess it's three fully connected layers. And so in these two fully connected layers at the start here, what we could do is we could delete some of the activations at random. And so this has happened here by X. This is what X means. It's like deleting those activations at random. And if we do so, you can see we end up with a lot less computation going on. And what dropout does is each mini batch, it randomly deletes a different set of activations from whatever layers you ask for. So that's what dropout does. So basically the idea is that dropout helps to generalize, because if a particular activation was kind of effectively learning some input, some particular piece of input, memorizing it, then sometimes it gets randomly deleted. And so then suddenly it's not going to do anything useful at all. So by randomly deleting activations, it ensures that activations can't become over-specialized at doing just one thing. Because then if it did, then the times they're randomly deleted, it's not going to work. So here is the entire implementation of a dropout layer. You pass it some value p, which is the probability that an activation gets deleted. So we'll store that away. And so then in the forward, you're going to get your activations. Now, if you're not training, so if you're doing validation, then we're not going to do dropout, right? But if we are training, then we create a mask. And so the mask is Bernoulli random a Bernoulli random variable. So what does Bernoulli random variable means? It means it's a bunch of ones and zeros where this is the probability that we get a 1, which is 1 minus the probability we get a 0. And so then we just multiply that by our input. So that's going to convert some of the inputs into zeros, which is basically deleting them. So you should check out some of the details, for example, about why we do a divide 1 minus p, which is described here. And we do point out here that normally, and I would normally in the lesson show you an example of what Bernoulli does. But of course nowadays, we're getting to the advanced classes, you're expected to do it yourself. So be sure to create a little cell here and make sure you actually create a tensor and then run Bernoulli underscore on it and make sure you see exactly what it's doing so that then you can understand this class. Now, of course, we don't have to use this class we made ourselves. We can just use nn.dropout. But you can use this class yourself because it does the same thing. So again, we're trying to make sure that we know how to build stuff from scratch. This special self.training is set for every module automatically by fast.ai based on whether or not you're in the validation part of your training loop or the training part of your training loop. It's also part of PyTorch, and in PyTorch, if you're not using fast.ai, you have to call the train method on a module to set training to true, and the eval method to set it to false for every module inside some other module. So that's one great approach to regularization. Another approach which I've only seen used in recurrent neural nets is activation regularization and temporal activation regularization, which is very, very similar to the question that we were just asked. What happens with activation regularization is it looks very similar to weight decay, but rather than adding some multiplier times the sum of squareds of the weights, we add some multiplier by the sum of squareds of the activations. So in other words, we're basically saying we're not just trying to decrease the weights, but decrease the total activations. And then similarly, we can also see what's the difference between the activations from the previous time step to this time step. So take the difference. And then again, squared times some value. So these are two hyperparameters, alpha and beta. The higher they are, the more regularized your model. And so with TAR, it's going to say no layer of the LSTM should too dramatically change the activations from one time step to the next. And then for alpha, it's saying no layer of the LSTM should create too large activations. And so they wouldn't actually create these large activations or large changes unless the loss improved by enough to make it worth it. Okay, so there's then, I think, just one more thing we need to know about, which is called weight tying. And weight tying is a very minor change, and let's have a look at it here. So this is the embedding we had before. This is the LSTM we had before. This is where we're going to introduce dropout. This is the hidden to output linear layer we had before. But we're going to add one more line of code, which is the hidden to output weights are actually equal to the input to hidden weights. Now, this is not just setting them once. This is actually setting them so that they're a reference to the exact same object in memory, the exact same tensor in memory. So the weights of the hidden to output layer will always be identical to the weights of the input to hidden layer. And this is called weight tying. And the reason we do this is because conceptually, in a language model, predicting the next word is about kind of converting activations into English words, whereas an embedding is about converting English words to activations. And there's a reasonable hypothesis, which would be that, well, those are basically exactly the same computation, or at least the reverse of it. So why shouldn't they use the same weights? And it turns out, lo and behold, yes, if you use the same weights, then actually it does work a little bit better. So then here's our forward, which is to do the input to hidden, do the RNN, apply the dropout, do the detach, and then apply the hidden to output, which is using exactly the same weights as the input to hidden, and resets the same. We haven't created the RNN regularizer from scratch here, but you can add it as a callback, passing in your alpha and your beta. If you call text learner instead of learner, it will add the model resetter and the RNN regularizer for you. So that's what one of the things text learner does. So this code is the same as this code. And so we can then train a model again, and let's also add weight decay. And look at this. We're getting up close to 90% accuracy. So we've covered a lot in this lesson. But the amazing thing is that we've just replicated all of the pieces in an AWD LSTM, all of the pieces in this state-of-the-art recurrent neural net, which we've showed we could use in the previous notebook to get what was until very recently state-of-the-art results for text classification, and far more quickly and with far less compute and memory than more modern than the approaches in the last year or so, which have beaten that benchmark. So this is a really efficient, really accurate approach, and it's still the state of the art in many academic situations, and it's still very widely used in industry. And so it's pretty cool that we've actually seen how to write it from scratch. So the main thing to mention in the further research is to have a look at the source code for AWD LSTM and fast.ai and see if you can see how the things in AWD-LSTM map to what those lines of code, how they map to the concepts that we've seen in this chapter. Rachel, do we have any questions? So here we have come to the conclusion of our, what was originally going to be 7 lessons and turned into 8 lessons. I hope that you've got a lot out of this. Thank you for staying with us. What a lot of people now do when they finish, or at least people who finish previous courses, is they go back to lesson 1 and try and repeat it, but doing a lot less looking at the notebooks, a lot more doing stuff from scratch yourself, and going deeper into the assignments. So that's one thing you could do next. Another thing you could do next would be to pick out a Kaggle competition to enter, or pick a book that you want to read about deep learning, or a paper, and team up with some friends to do like a paper reading group or a book reading group. One of the most important things to keep the learning going is to get together with other people on the learning journey. Another great way to do that, of course, is through the forums. So if you haven't been using the forums much so far, no problem, but now might be a great time to get involved and find some projects that are going on that look interesting. And it's fine if you don't have to be an expert, right? Obviously, any of those projects, the people that are already doing it are going to know more about it than you do at this point because they're already doing it. But if you drop into a thread and say, hey, I would love to learn more about this, how do I get started? Or have a look at the wiki posts to find out and try things out. You can start getting involved in other people's projects and help them out. And of course, don't forget about writing. So if you haven't tried writing a blog post yet, maybe now's a great time to do that. Pick something that's interesting to you, especially if it's something in your area of expertise at work or a hobby or something like that, or specific to where you live. Maybe you could try and build some kind of text classifier or text generator for particular kinds of text that you know about. That would be a super interesting thing to try out, and be sure to share it with the folks on the forum. So there's a few ideas. So don't let this be the end of your learning journey. Keep going, and then come back and try part 2 if it's not out yet. Obviously, you'll have to wait until it is out. But if it is out, you might want to kind of spend a couple of months, really experimenting with this before you move on to part 2 to make sure that everything in part 1 feels pretty solid to you. Well, thank you very much, everybody, for your time. We've really enjoyed doing this course. It's been a tough course for us to teach because with all this COVID-19 stuff going on at the same time, I'm really glad we've got through it. I'm particularly grateful to Sylvain, who has been extraordinary in really making so much of this happen, and particularly since I've been so busy with COVID-19 stuff around masks in particular. It's really a lot thanks to Sylvain that everything's come together. And of course to Rachel, who's been here with me on every one of these lessons. Thank you so much. And I'm looking forward to seeing you again in a future course. Thanks, everybody.